When physics lost its mind, the comfortable certainties of classical science crumbled beneath the weight of experimental evidence that revealed a universe far stranger than anyone had imagined, where particles could exist in multiple places simultaneously, where the act of observation fundamentally altered reality, and where the very notion of objective physical properties independent of conscious observers began to seem like a naive assumption from a simpler time when scientists believed they could study reality without fundamentally disturbing it. The quantum revolution that began in the early 20th century didn't merely introduce new theories or mathematical formalism, it shattered the conceptual foundations upon which the entire scientific enterprise had been built, forcing physicists to confront the possibility that their most basic assumptions about the nature of reality, causation, and objective knowledge might be fundamentally flawed. The double-slit experiment stands as the paradigmatic demonstration of quantum weirdness, revealing that individual photons or electrons behave as waves when unobserved, creating interference patterns that suggest they pass through both slits simultaneously, yet behave as particles when observed, passing through only one slit and destroying the interference pattern through the mere act of measurement. This experiment demonstrates that quantum systems exist in superposition states of all possible outcomes until the moment of observation forces them to choose a definite state, suggesting that reality at the quantum level remains fundamentally indeterminate until consciousness or measurement apparatus intervenes to collapse the wave function into a single classical outcome. The implications of this phenomenon extend far beyond technical physics into fundamental questions about the nature of reality itself. Wave-particle duality forced physicists to abandon the classical assumption that objects possess definite properties independent of observation, revealing instead that quantum entities exhibit different characteristics depending on how they are observed, measured, or detected, creating a situation where the properties of reality appear to depend on the experimental context and measurement procedures rather than existing as intrinsic features of an objective physical world. This contextual nature of quantum properties suggests that reality might not possess the independent, determinate character that classical physics assumed, but instead might be fundamentally relational, existing only in the interactions between quantum systems and measurement apparatus, rather than as autonomous entities with definite properties. Quantum superposition demonstrates that particles can exist in combinations of multiple states simultaneously, with quantum systems maintaining coherent combinations of all possible states until measurement forces them into definite classical configurations through wave function, collapse mechanisms that remain poorly understood despite decades of intensive theoretical and experimental investigation. The persistence of quantum superposition in increasingly large and complex systems continues to challenge classical intuitions about the definiteness and determinacy of physical reality, while suggesting that the classical world of definite objects and properties might emerge from more fundamental quantum indeterminacy through measurement and observation processes that operate according to principles that transcend classical physics. The uncertainty principle reveals fundamental limits on the precision with which complementary properties like position and momentum can be simultaneously determined, suggesting that these limitations reflect not merely practical constraints on measurement technology, but fundamental features of quantum reality, where properties do not possess definite values independent of measurement contexts. Heisenberg's uncertainty relations indicate that quantum systems do not possess the complete set of definite properties that classical physics attributed to physical objects, creating situations where the very concept of a particle having both definite position and definite momentum simultaneously becomes meaningless within quantum theoretical frameworks. Observer effects in quantum mechanics extend far beyond simple measurement disturbance to include fundamental alterations in the properties and behavior of quantum systems through the act of observation itself, creating scenarios where observers appear to participate in determining the outcomes of quantum processes rather than passively recording predetermined results from an independent objective reality. The quantum measurement problem involves understanding how and why conscious observational measurement apparatus triggers wave function, collapse while ordinary physical interactions between quantum systems do not produce the same definitive outcomes, suggesting that measurement represents a fundamentally different type of physical process that transcends normal quantum mechanical interactions. Delayed choice experiments demonstrate that decisions about measurement procedures can retroactively determine the past behavior of quantum systems, with photons appearing to decide whether they behaved as waves or particles based on measurement choices made after they had already interacted with experimental apparatus, suggesting that quantum systems might not possess definite histories independent of future measurement decisions. These temporal aspects of quantum measurement create profound challenges for classical assumptions about causation and temporal order, while indicating that quantum reality might not unfold according to determinate causal sequences that proceed from past to future without reference to future events and measurement choices. Quantum entanglement reveals that quantum systems can become correlated in ways that transcend spatial separation, with measurements performed on one particle instantaneously affecting the properties of distant entangled partners, regardless of the spatial distance separating them, creating spooky action at a distance that violates classical assumptions about locality and the independence of spatially separated objects. These non-local correlations suggest that quantum reality operates according to holistic principles where spatially separated systems remain fundamentally connected through quantum mechanical relationships that transcend classical space-time limitations and challenge basic assumptions about the independent existence of localized physical objects. The measurement apparatus problem involves understanding why macroscopic measurement devices produce definite classical outcomes when they are composed of quantum components that should themselves exist in superposition states, creating an infinite regress where every measurement device requires another measurement device to determine its state, ultimately suggesting that the transition from quantum indeterminacy to classical definiteness requires something beyond purely physical processes. This problem highlights the conceptual difficulties involved in understanding how the classical world of definite objects and properties emerges from quantum foundations that appear to lack these classical characteristics. Interpretation proliferation in quantum mechanics reflects the deep conceptual challenges posed by quantum phenomena, with major interpretations including Copenhagen, many worlds, pilot wave, spontaneous collapse, and consciousness-based approaches offering radically different views of reality's fundamental nature, while remaining empirically equivalent in their predictions for experimental outcomes. The persistence of multiple viable interpretations after nearly a century of quantum mechanics suggests that the conceptual foundations of physical reality remain fundamentally unsettled despite the remarkable empirical success of quantum theoretical predictions and technological applications. The transition from classical to quantum physics represents more than a shift in scientific theories. It constitutes a fundamental transformation in humanity's understanding of the relationship between mind and reality, subject and object, observer and observed, revealing that the clear distinctions that seem to characterize classical physical reality might be conceptual artifacts of limited perspectives rather than fundamental features of reality itself. This transformation has forced scientists to confront the possibility that objective reality independent of consciousness might not exist in the form that classical physics assumed while opening new questions about the role of consciousness in physical processes. The irony minds like the physics itself. The scientific method designed to reveal objective truth about reality independent of human subjectivity led to discoveries that call into question the very possibility of objective reality independent of observation and consciousness. While the more precisely scientists investigated the fundamental nature of physical reality, the more elusive and observer-dependent that reality appeared to become, creating a situation where the most successful scientific theory in history undermines the basic assumptions upon which scientific objectivity was originally founded, suggesting that understanding reality might require abandoning the classical separation between observer and observed that enabled scientific methodology while embracing more integrated approaches that recognize consciousness as a fundamental component of physical reality rather than an accidental byproduct of complex matter. The measurement problem's deepening mystery haunts quantum mechanics like an unresolved philosophical spectre, representing perhaps the most fundamental challenge to our understanding of physical reality as scientists struggle to explain how and why quantum systems transition from superposition states containing multiple simultaneous possibilities to definite classical outcomes through measurement processes that remain conceptually opaque, despite decades of theoretical investigation and experimental refinement. This transition from quantum indeterminacy to classical definiteness appears to require something beyond ordinary physical processes. Yet no mechanism has been identified that can account for wave function collapse without introducing additional assumptions about consciousness. Hidden variables, or exotic physical processes that transcend standard quantum mechanical formalism while maintaining consistency with experimental observations. Wave function collapse represents the most dramatic and mysterious aspect of quantum measurement, involving the instantaneous transition from a quantum superposition containing all possible measurement outcomes to a single definite classical result that appears to occur faster than light and without any identifiable physical mechanism responsible for selecting one particular outcome from the infinite range of quantum possibilities. The collapse process appears to violate several fundamental principles of physics, including energy conservation during the transition, the continuity of physical processes, and the locality of causal influences. Yet, experimental evidence consistently demonstrates that quantum measurements produce definite outcomes, rather than the indefinite superposition states that quantum mechanical equations predict should persist indefinitely without external intervention. The von Neumann-Wigner interpretation proposes that consciousness serves as the agent responsible for wave function collapse, suggesting that conscious observation represents a fundamentally different type of physical process that can reduce quantum superposition states to definite classical outcomes through mechanisms that transcend ordinary physical interactions between material systems. This consciousness-based approach to quantum measurement solves the infinite regress problem by identifying consciousness as the ultimate measurement device that does not itself require measurement by another system. Yet it introduces profound questions about the relationship between mind and matter, while implying that consciousness possesses causal efficacy in physical processes that transcends purely material mechanisms. Many worlds' interpretation attempts to eliminate wave function collapse entirely by proposing that all possible quantum outcomes actually occur in parallel universe branches, with conscious observers experiencing only one branch while remaining unaware of alternative outcomes that unfold simultaneously in inaccessible parallel realities. This interpretation preserves the deterministic evolution of the universal wave function while explaining the appearance of random measurement outcomes through observer selection effects that limit conscious awareness to single branches of the universal quantum state. Yet it multiplies the ontological complexity of reality by requiring infinite numbers of parallel universes while failing to explain why conscious experience appears limited to single branches rather than encompassing multiple parallel outcomes. Pilot wave theories maintain that particles possess definite positions and momenta at all times while being guided by quantum wave functions that determine their trajectories through deterministic but non-local mechanisms that reproduce quantum mechanical predictions without requiring wave function collapse or observer-dependent reality. These hidden variable approaches restore classical definiteness to quantum systems while maintaining deterministic causation, yet they require instantaneous non-local interactions between distant quantum systems that appear to violate relativity while introducing unobservable hidden variables that cannot be directly detected or verified through experimental investigation, creating theories that are empirically equivalent to standard quantum mechanics but conceptually very different. Spontaneous collapse theories propose that wave function collapse occurs randomly and objectively through physical processes that operate independently of observation or consciousness, with quantum superposition states naturally decaying into definite classical states through stochastic mechanisms that become more probable for larger and more complex quantum systems. These objective collapse models attempt to provide physical mechanisms for wave function reduction, while explaining the transition from quantum to classical behavior through spontaneous localization processes. Yet they require modifications to standard quantum mechanics that have not been experimentally confirmed, while introducing random elements into physical processes that conflict with the deterministic character of quantum mechanical evolution. The quantum to classical transition remains poorly understood despite its fundamental importance for understanding how the definite classical world emerges from quantum foundations that appear to lack classical properties like definiteness, locality, and objective existence independent of observation. Decoherence theory explains how quantum superposition states become effectively classical through interactions with environmental systems that destroy quantum coherence. Yet decoherence cannot explain why measurement outcomes appear definite rather than remaining in reduced density. Matrix states that maintain quantum superposition characteristics despite environmental interactions that eliminate coherence effects. Measurement apparatus analysis reveals that every quantum measurement requires classical measurement devices that themselves are composed of quantum components, creating conceptual difficulties in understanding how classical definiteness emerges from quantum indefiniteness, without invoking infinite chains of measurement devices that require other measurement devices to determine their states. The boundary between quantum and classical systems appears arbitrary and context-dependent, rather than reflecting fundamental physical distinctions, suggesting that the quantum classical distinction might be conceptual rather than ontological, while highlighting the problems involved in understanding measurement processes within purely physical frameworks. Schrödinger's cat paradox illustrates the conceptual difficulties involved in applying quantum mechanics to macroscopic systems, revealing the absurdity of extending quantum superposition to everyday objects while highlighting the problems involved in understanding where and why the transition from quantum to classical behavior occurs during measurement processes. The cat cannot be simultaneously alive and dead in any meaningful sense. Yet quantum mechanics appears to predict such superposition states for unobserved macroscopic systems, creating paradoxes that have never been satisfactorily resolved despite numerous attempts to clarify the relationship between quantum and classical descriptions of physical reality. Quantum measurement theory attempts to provide rigorous mathematical frameworks for understanding measurement processes, while identifying the precise conditions under which quantum systems transition from superposition states to definite classical outcomes. Yet these theoretical approaches often invoke additional assumptions about consciousness, environmental decoherence, or spontaneous collapse mechanisms that go beyond standard quantum mechanical formalism. The mathematical formalism of quantum mechanics provides precise predictions for measurement probabilities while remaining silent about the physical mechanisms responsible for actualizing specific outcomes from quantum probability distributions, creating gaps between mathematical description and physical understanding. Bell's theorem and experimental violations of Bell inequalities demonstrate that any complete description of quantum systems must abandon either locality or realism, forcing physicists to choose between giving up the assumption that physical properties exist independently of measurement, or accepting that quantum systems can influence each other instantaneously across arbitrary distances. These experimental results constrain possible solutions to the measurement problem while eliminating entire classes of hidden variable theories that attempt to restore classical definiteness to quantum systems through local realistic mechanisms that maintain observer-independent physical properties. Contemporary research in quantum foundations continues to explore novel approaches to the measurement problem, including relational quantum mechanics, quantum Bayesianism, and information-theoretic interpretations that attempt to resolve measurement difficulties through new conceptual frameworks that reinterpret the meaning of quantum states, measurement outcomes, and physical reality itself. These research programs reflect ongoing dissatisfaction with existing interpretations while demonstrating the continued vitality of foundational research in quantum mechanics despite the theory's remarkable empirical success and technological applications. The irony problems, like the measurements themselves, The most precise and successful scientific theory in history cannot explain its most basic and essential process: how definite measurement outcomes emerge from quantum possibilities. While the attempt to understand quantum measurement reveals that the concepts of objective reality, definite properties, and observer-independent existence that underlie scientific methodology might be fundamentally incompatible with the quantum mechanical description of nature, creating a situation where the foundation of modern physics rests on measurement processes that remain as mysterious today as they were when quantum mechanics was first formulated, suggesting that resolving the measurement problem might require abandoning basic assumptions about the nature of physical reality and scientific knowledge that have guided scientific investigation for centuries. Bell's theorem and the death of local realism delivered a fatal blow to classical physics' most fundamental assumptions about reality, proving mathematically that no physical theory based on local realistic principles can reproduce the predictions of quantum mechanics, while subsequent experimental violations of Bell inequalities have confirmed that nature herself violates these classical principles, forcing physicists to abandon either the assumption that physical properties exist independently of measurement, realism, or the principle that influences cannot propagate faster than light locality. This profound result means that the universe operates according to principles that transcend classical intuitions about separated objects possessing definite properties that evolve through local causal interactions, revealing instead a reality where spatially separated quantum systems remain fundamentally connected through non-local correlations that challenge basic assumptions about the independence of distant physical events and the objective existence of physical properties. Einstein-Podolsky-Rosen paradox originally attempted to demonstrate the incompleteness of quantum mechanics by showing that quantum theory led to seemingly absurd conclusions about spatially separated particles instantaneously affecting each other's properties without any causal mechanism connecting them across space. A phenomenon Einstein dismissed as spooky action at a distance that violated fundamental principles of locality and causality that had guided classical physics for centuries. EPR argued that if quantum mechanics were complete, then measuring one particle would instantaneously determine the properties of its distant partner, which seemed physically impossible, leading them to conclude that quantum mechanics must be incomplete and that hidden variables must exist to restore local realistic explanations for quantum correlations while preserving classical assumptions about objective reality. Bell's mathematical proof demonstrated that any theory based on local hidden variables must satisfy specific mathematical constraints, Bell inequalities, that limit the strength of correlations between spatially separated measurements. While quantum mechanics predicts correlations that violate these inequalities under certain experimental conditions, creating a testable distinction between local realistic theories and quantum mechanical predictions, Bell's insight revealed that the EPR critique of quantum mechanics could be resolved experimentally by performing measurements that would distinguish between local hidden variable theories and quantum mechanics, transforming a philosophical debate about the interpretation of quantum mechanics into an empirical question that could be settled through carefully designed experiments. Aspects experiments in the 1980s provided the first convincing demonstrations that Bell inequalities are indeed violated in nature, with measurements of entangled photon pairs showing correlations that exceed the limits possible for any local realistic theory, while confirming quantum mechanical predictions with high statistical significance. These experimental results eliminated entire classes of hidden variable theories while establishing that quantum non-locality represents a genuine feature of nature rather than an artifact of incomplete theoretical description, forcing physicists to accept that reality operates according to non-local principles that transcend classical space-time limitations on causal influences and information propagation. Quantum entanglement creates correlations between spatially separated particles that transcend any classical explanation based on local interactions or pre-existing properties, with entangled systems exhibiting coordinated behaviors that appear to require instantaneous communication or coordination across arbitrary distances without any identifiable mechanism for transmitting influences between separated locations. These entanglement correlations cannot be explained by assuming that particles carry predetermined properties that determine measurement outcomes. Since Bell inequality violations prove that no set of predetermined properties can account for the strength of quantum correlations observed in experiments with entangled systems, non-locality versus non-realism presents physicists with a forced choice between abandoning locality, accepting that influences can propagate instantaneously across space, or abandoning realism, accepting that physical properties do not exist independently of measurement. With both options representing profound departures from classical physics that require fundamental revisions to basic assumptions about the nature of physical reality and causal relationships. Locality violations would require accepting action at a distance mechanisms that operate faster than light and potentially outside normal space-time frameworks, while realism violations would require accepting that physical properties emerge only through measurement interactions rather than existing as intrinsic features of autonomous physical objects. Superdeterminism represents one potential loophole in Bell's theorem that could preserve local realism by proposing that measurement choices and particle properties are correlated through common causal origins that predetermine both experimental configurations and measurement outcomes. Eliminating the freedom of choice required for Bell's proof while maintaining local realistic explanations for quantum correlations. However, superdeterministic theories require giving up experimental freedom and causal independence in ways that undermine the entire scientific enterprise by making controlled experimentation impossible if measurement choices are predetermined by the same causal factors that determine experimental outcomes. Loophole-free Bell tests have progressively closed experimental loopholes that could potentially allow local, realistic explanations for observed Bell inequality violations, including detection efficiency loopholes, locality loopholes, and freedom of choice loopholes that might enable local hidden variable theories to mimic quantum mechanical predictions through experimental artifacts rather than genuine non-local correlations. Contemporary Bell experiments achieve simultaneous closure of all major loopholes while maintaining Bell inequality violations with overwhelming statistical significance, providing definitive experimental evidence that nature violates local realism while confirming the non-local character of quantum mechanical correlations. Quantum field theory. Implications of Bell's theorem extend non-locality to relativistic quantum field theory contexts, where locality violations must be reconciled with special relativity constraints on causal influences and information propagation, creating tensions between quantum non-locality and relativistic causality that remain incompletely understood despite decades of theoretical investigation. Quantum field theory manages to preserve relativistic causality for observable quantities while maintaining non-local quantum correlations through subtle mechanisms that prevent the use of quantum entanglement for faster-than-light communication. Yet the conceptual foundations of this compatibility remain controversial and poorly understood. Many worlds interpretations attempt to preserve locality by proposing that Bell inequality violations reflect correlations between parallel universe branches rather than genuine non-local influences within single universe branches, with measurement outcomes determined by which branch observers find themselves in, rather than by non-local causal influences between spatially separated quantum systems. This approach maintains local realistic descriptions within individual branches while attributing apparent non-locality to cross-branch correlations that do not involve causal influences within any single branch. Yet it multiplies ontological complexity by requiring infinite parallel realities while failing to explain branch selection mechanisms. Retrocausal interpretations propose that future measurement choices influence past quantum states through backward-in-time causal influences that could account for Bell inequality violations without requiring faster-than-light spatial influences, suggesting that quantum correlations reflect temporal rather than spatial non-locality through retrocausal mechanisms that connect future measurement events to past quantum state preparations. These interpretations attempt to preserve spatial locality while accepting temporal non-locality, Yet they require radical revisions to classical assumptions about temporal causality and the relationship between past and future events that challenge fundamental concepts about time and causation. Information theoretic approaches to Bell's theorem focus on the non-local correlations as fundamental features of information processing rather than material causation, suggesting that quantum non-locality reflects informational rather than causal connections between spatially separated quantum systems that share correlated information without requiring causal influences or material interactions. These information-based interpretations treat quantum correlations as fundamental features of information structure rather than mysterious causal mechanisms. Yet they leave unresolved questions about the relationship between information and physical reality, while potentially dissolving rather than solving conceptual problems about quantum non-locality. The irony localizes like the realism itself. Bell's theorem proves that the most basic assumptions of classical physics about local realistic properties cannot be maintained in a quantum world. Yet physicists must continue to use classical concepts and measurement apparatus to investigate quantum phenomena, creating a fundamental tension between the quantum reality being studied and the classical framework required for scientific investigation, while the death of local realism eliminates the conceptual foundations that originally motivated scientific methodology based on objective observation of independently existing reality, suggesting that understanding quantum reality might require developing entirely new approaches to scientific knowledge that abandon classical assumptions about observer-independent reality, while somehow maintaining the possibility of reliable knowledge about quantum systems that appear to lack the definite properties that classical science attempted to measure and understand. The hard problem of consciousness represents perhaps the most profound challenge to scientific materialism, as researchers struggle to explain how subjective experience emerges from objective neural processes, creating fundamental disagreements about whether consciousness represents an irreducible feature of reality that cannot be explained through purely physical mechanisms, or whether subjective experience will eventually yield to reductionist explanations that treat consciousness as complex information processing and biological systems. This explanatory gap between objective neural activity and subjective conscious experience has resisted decades of intensive neuroscientific investigation, while revealing deep conceptual problems about the relationship between mind and matter that challenge the materialist assumptions underlying modern science and force researchers to confront the possibility that consciousness might represent a fundamental aspect of reality, rather than an emergent property of complex physical systems. Qualia represent the irreducible qualitative aspects of conscious experience, including the redness of red, the pain of pain, and the joy of joy that appear to possess properties that cannot be captured through objective physical description, regardless of how detailed or sophisticated such descriptions become, suggesting that conscious experience involves non-physical properties that transcend material processes, while potentially serving as evidence that consciousness operates according to principles that lie beyond the scope of purely physicalist scientific investigation. These qualitative aspects of experience remain private and subjective, accessible only to the experiencing subject, creating an epistemic barrier that prevents objective scientific methodology from directly accessing or studying the most essential features of consciousness, while highlighting fundamental limitations in scientific approaches to understanding subjective phenomena. Neural correlates of consciousness research attempts to identify the specific brain processes that correspond to different aspects of conscious experience, while revealing complex relationships between neural activity and subjective states that suggest consciousness involves sophisticated information integration and coordination across multiple brain regions and temporal scales. However, correlation does not establish causation, and the identification of neural correlates fails to explain how or why neural processes generate subjective experience rather than simply producing complex information processing without accompanying awareness. Leaving the fundamental question of conscious experience unexplained, despite remarkable advances in understanding the neural mechanisms associated with different conscious states and cognitive functions, the binding problem in neuroscience acknowledges that conscious experience appears unified and integrated despite being processed by distributed neural networks that operate across different brain regions, temporal scales, and processing streams, creating challenges for understanding how separate neural processes combine to create coherent conscious experiences that transcend the spatial and temporal boundaries of individual neural components. The apparent unity of consciousness suggests that conscious experience involves integration mechanisms that operate according to principles that might transcend purely neural processing while creating coherent conscious states from distributed neural activities through mechanisms that remain poorly understood despite intensive research into neural integration and binding processes. Emergence versus reduction debates in consciousness research involve fundamental disagreements about whether conscious experience represents genuinely emergent properties that cannot be reduced to purely physical processes, or whether consciousness will eventually be explained through detailed understanding of neural mechanisms without requiring non-physical properties or processes. Strong emergence would suggest that consciousness involves causal powers that transcend the causal powers of underlying neural components, while reductive approaches maintain that consciousness will ultimately be explained through complete understanding of neural processing without requiring emergent properties that transcend physical causation, creating fundamental disagreements about the ontological status of conscious experience. Panpsychist approaches to consciousness propose that consciousness represents a fundamental property of all matter, rather than an emergent property of complex neural systems, suggesting that elementary particles possess rudimentary conscious properties that combine and integrate through physical interactions to create the complex conscious experiences associated with biological brains, while eliminating the hard problem by treating consciousness as a basic feature of reality rather than something that needs to emerge from unconscious components. This perspective treats consciousness as analogous to fundamental physical properties like mass or charge, while requiring new frameworks for understanding how simple conscious properties combine to create complex conscious experiences without losing essential conscious characteristics. Information integration theory attempts to quantify consciousness through mathematical measures of information integration that identify conscious systems as those capable of generating high levels of integrated information, while distinguishing conscious from unconscious information processing through specific organizational patterns that create unified conscious experiences from diverse information sources. This approach treats consciousness as a measurable property of information processing systems, while providing frameworks for understanding different levels and types of consciousness across biological and potentially artificial systems. Yet it remains unclear whether information integration captures the essential features of subjective experience or merely identifies complex information processing patterns. Global workspace theory proposes that consciousness involves global broadcasting of information across distributed neural networks that enable different brain systems to access and share information through conscious awareness that serves as a central information integration and coordination mechanism for complex cognitive processing. This approach treats consciousness as a particular type of information processing architecture, rather than a mysterious non-physical phenomenon. Yet it fails to explain why global information integration should be accompanied by subjective experience, rather than simply enabling sophisticated unconscious information processing and behavioral coordination without conscious awareness. Free will and consciousness involve questions about whether conscious experience includes genuine agency and causal efficacy that enables conscious entities to influence physical processes through conscious intention and decision-making that transcends purely deterministic physical causation. The apparent experience of free will creates challenges for materialist explanations of consciousness that must either explain free will as an illusion created by complex neural processing or acknowledge that consciousness involves causal powers that transcend purely physical determinism, while enabling genuine choice and moral responsibility through conscious agency that operates beyond mechanical causation. Machine consciousness possibilities involve questions about whether artificial intelligence systems could develop genuine conscious experience rather than merely simulating conscious behavior through sophisticated information processing that lacks subjective awareness. creating debates about the criteria for recognizing consciousness in artificial systems and the relationship between consciousness and computational processing. The development of increasingly sophisticated AI systems raises questions about consciousness detection and the ethical implications of potentially conscious artificial entities, while highlighting uncertainties about the essential features that distinguish conscious from unconscious information processing systems. Altered states of consciousness research reveals that conscious experience can be dramatically modified through meditation, psychedelic substances, brain stimulation, and various other interventions that alter neural activity while creating profound changes in subjective experience that sometimes include experiences of unity, timelessness, and dissolution of self, other boundaries that challenge conventional assumptions about consciousness and reality. These altered states suggest that normal conscious experience represents one possible configuration among many potential conscious states, while raising questions about the relationship between neural activity and subjective experience that transcend normal waking consciousness. Consciousness and quantum mechanics connections have been proposed by some researchers who suggest that quantum mechanical effects in neural microtubules or other biological structures might enable consciousness to access quantum computational resources or operate according to quantum mechanical principles that transcend classical neural processing limitations. However, these quantum consciousness theories remain highly speculative and controversial, with most neuroscientists maintaining that brain temperature and environmental decoherence prevent significant quantum effects in neural processing, while arguing that classical neural mechanisms provide sufficient explanatory resources for understanding consciousness without requiring quantum mechanical explanations. The irony problems like consciousness itself, the scientific method designed to study objective reality, encounters its greatest challenge when attempting to understand subjective conscious experience that cannot be directly observed or measured through objective methodologies. While consciousness represents both the foundation that enables all scientific investigation and the phenomenon that most resists scientific explanation, creating a situation where the very capacity that enables scientific knowledge remains the most mysterious aspect of reality from a scientific perspective, suggesting that understanding consciousness might require developing new approaches to knowledge that integrate subjective and objective perspectives while somehow maintaining scientific rigor and empirical grounding in investigations of phenomena that transcend purely objective analysis and measurement. Information versus matter represents a fundamental battleground in contemporary physics, where growing evidence suggests that reality might be fundamentally informational rather than material, with some physicists proposing that the universe operates as a vast computational process where what we perceive as matter and energy emerge from underlying information processing patterns that transcend traditional materialist frameworks, while potentially revealing that physical reality consists of information structures rather than substantial material entities that exist independently of information processing relationships. This digital physics paradigm treats computation and information as more fundamental than matter and energy, while suggesting that the apparent material world emerges from computational processes operating at scales and levels that remain largely invisible to ordinary observation, yet determine the structure and evolution of physical reality through informational mechanisms. Wheeler's it from bit hypothesis proposes that all physical entities and phenomena emerge from binary information processing, with every material particle, force, and physical property deriving from underlying yes or no answers to binary questions that constitute the fundamental information processing operations from which physical reality emerges through computational mechanisms that operate at the most basic level of natural processes. This information theoretic approach treats physical properties as emergent features of information processing, rather than fundamental characteristics of material substances, while suggesting that understanding reality requires focusing on information patterns and computational relationships, rather than material particles and forces that might represent higher-level emergent phenomena. Computational physics models demonstrate that complex physical phenomena, including fluid dynamics, crystal formation, and ecosystem evolution can be accurately simulated through computational processes that reproduce natural patterns and behaviors through algorithmic rules operating on digital information structures. Suggesting that natural phenomena might actually operate through computational mechanisms rather than merely being amenable to computational modeling and simulation techniques. The success of computational models in reproducing natural phenomena raises questions about whether nature itself operates computationally, while potentially indicating that the distinction between natural processes and computational simulations might be less fundamental than typically assumed. Digital physics theories propose that space-time itself operates through discrete computational processes rather than continuous mathematical functions, with space and time emerging from underlying digital information processing that operates through finite computational steps rather than infinite mathematical precision, creating frameworks where physical reality consists of discrete information processing units that generate the appearance of continuous space-time through computational operations at extremely small scales and high frequencies. These discrete approaches to space-time suggest that reality might be fundamentally digital rather than analog, while potentially explaining various quantum mechanical phenomena through computational mechanisms that operate at the Planck scale. Cellular automata research reveals that simple computational rules operating on discrete information grids can generate complex patterns and behaviors that resemble natural phenomena, including crystal growth, biological development, and fluid turbulence, demonstrating that computational information processing can produce the organized complexity that characterizes natural systems without requiring material substrates or continuous mathematical dynamics. The ability of cellular automata to generate natural patterns suggests that similar computational processes might underlie actual natural phenomena, while providing frameworks for understanding how complex reality emerges from simple information processing rules. Quantum information theory treats quantum mechanics as fundamentally concerned with information processing rather than material particles, with quantum states representing information configurations and quantum evolution involving information transformation processes that enable quantum systems to process and manipulate information in ways that transcend classical computational limitations, while revealing new perspectives on the relationship between information and physical reality. This information theoretic approach to quantum mechanics suggests that quantum phenomena involve information processing mechanisms that operate according to quantum computational principles rather than classical material interactions. Entropy and information connections reveal deep relationships between thermodynamic entropy and information entropy that suggest physical processes involve information processing mechanisms where energy dissipation corresponds to information destruction, and organized structures correspond to information storage and processing capabilities that enable complex systems to maintain organization against thermodynamic decay through information processing activities. These entropy-information relationships indicate that physical and informational processes might be more closely related than classical physics assumed, while suggesting that understanding physical reality requires considering information processing aspects of natural phenomena. Holographic information storage principles demonstrate that complete information about three-dimensional volumes can be encoded on two-dimensional surfaces, suggesting that spatial reality might emerge from information processing on lower-dimensional substrates rather than existing as fundamental three-dimensional structures, creating possibilities that apparent spatial extension emerges from information processing patterns rather than representing basic features of physical reality. The holographic principle in physics proposes that all information in gravitational systems is encoded on boundary surfaces, while three-dimensional space emerges from information processing on these boundaries. Mathematical reality versus physical reality debates involve questions about whether mathematical structures exist independently of physical instantiation, while potentially serving as the fundamental reality from which physical phenomena emerge through mathematical relationships, rather than mathematics simply providing descriptive tools for understanding independently existing material reality. Platonic mathematical realism suggests that mathematical structures possess objective existence, while physical reality emerges from mathematical relationships. Creating frameworks where information processing and computational relationships represent the fundamental reality underlying apparent material phenomena. Consciousness as information processing proposes that conscious experience involves sophisticated information integration and processing that might operate according to computational principles while potentially enabling consciousness to exist in artificial systems capable of sufficient information, processing complexity and integration patterns. This computational approach to consciousness treats subjective experiences emerging from particular types of information processing while suggesting that consciousness might be substrate independent and potentially implementable in artificial systems that achieve appropriate information processing architectures. Simulation hypothesis implications suggest that if reality is fundamentally informational, then the distinction between natural reality and artificial simulation becomes problematic, since both involve information processing systems that generate coherent experiential realities for conscious observers embedded within information processing environments. The possibility that our reality represents a sophisticated simulation running on computational substrates highlights questions about the fundamental nature of reality while suggesting that information processing might be more fundamental than material substance. Network reality theories propose that reality consists of information processing networks, where apparent material objects and spatial relationships emerge from network connectivity patterns and information flow dynamics rather than representing fundamental material entities existing in independent spatial frameworks. These network approaches treat reality as consisting of relationships and information processing patterns rather than substantial entities, while suggesting that understanding reality requires analyzing network structures and information processing dynamics rather than material properties and spatial configurations. The irony processes like the information itself. The attempt to reduce reality to purely material components encounters growing evidence that information processing might be more fundamental than material substance. While the digital revolution in technology reveals new possibilities for understanding reality through computational and informational frameworks that transcend traditional materialist assumptions, creating situations where the distinction between real and simulated, natural and artificial, material and informational becomes increasingly problematic as information processing capabilities advance and our understanding of natural information processing mechanisms deepens, suggesting that resolving questions about the fundamental nature of reality might require abandoning traditional matter-based ontologies in favor of information-based frameworks that treat computation and information processing as the fundamental reality from which apparent material phenomena emerge through complex information processing patterns and computational relationships that operate at multiple scales and levels of organization. The simulation hypothesis gains ground as technological advancement reveals the increasing plausibility that advanced civilizations could create realistic simulations indistinguishable from base reality, leading philosophers and physicists to seriously consider whether our own reality might be artificial rather than fundamental. While statistical arguments suggest that if civilizations develop powerful simulation capabilities, the number of simulated beings would vastly outnumber beings in base reality, making it statistically more likely that any given conscious observer exists within a simulation rather than fundamental reality. This hypothesis transforms from science fiction speculation into legitimate philosophical and scientific inquiry as computer processing power approaches levels that could theoretically support conscious beings within artificial environments while raising profound questions about the nature of reality, knowledge, and existence that challenge basic assumptions about the relationship between natural and artificial phenomena. Technological trajectory analysis reveals exponential growth in computational power that approaches scales where simulating conscious beings within artificial environments becomes theoretically possible. With advances in artificial intelligence, virtual reality, and quantum computing suggesting that technological civilizations might eventually develop capabilities for creating simulated universes populated by conscious entities who remain unaware of their artificial nature. The continuation of current technological trends could enable future civilizations to simulate entire universes, including conscious observers, while consuming relatively modest computational resources compared to total civilizational computing capabilities, making universe simulation a plausible activity for sufficiently advanced technological societies. Ancestor simulations represent one specific version of the simulation hypothesis, where advanced future humans create detailed simulations of their historical predecessors, potentially including simulated versions of early 21st century civilization populated by conscious beings who experience authentic subjective lives within historically accurate artificial environments. These ancestor simulations could serve various purposes, including historical research, entertainment, or cultural preservation, while creating numerous simulated conscious beings for every person who actually lived during the simulated historical period, dramatically increasing the total population of conscious beings throughout history if such simulations become common practice among advanced civilizations. Bostrom's trilemma argues that at least one of three propositions must be true. Civilizations typically go extinct before developing advanced simulation capabilities. Advanced civilizations choose not to run ancestor simulations, or we are almost certainly living in a computer simulation ourselves, since if advanced civilizations commonly run ancestor simulations, simulated beings would vastly outnumber non-simulated beings throughout cosmic history. This statistical argument transforms the simulation hypothesis from a mere possibility into a statistical likelihood if we accept that civilizations can develop simulation capabilities and that some would choose to use them, creating probabilistic frameworks for evaluating the likelihood of existing within simulated rather than base reality. Computational substrate independence suggests that consciousness depends on information processing patterns rather than specific material substrates, enabling conscious experience to exist in silicon-based computers, quantum computing systems, or other artificial platforms capable of supporting sufficient computational complexity and information integration patterns. If consciousness is substrate independent, then artificial beings within sufficiently sophisticated simulations could possess genuine conscious experience rather than merely simulating conscious behavior, making simulated reality as experientially valid as base reality for conscious beings embedded within simulation environments, while eliminating qualitative distinctions between natural and artificial conscious experience. Nested simulation scenarios involve simulated beings themselves developing simulation technologies that enable them to create their own simulated universes populated by conscious entities, creating hierarchical chains of nested simulations where beings at each level remain unaware of higher-level simulation environments, while potentially creating lower-level simulated realities for their own purposes. These nested hierarchies could extend through multiple levels of simulation, while enabling conscious beings at any level to experience authentic, subjective lives regardless of their position within the simulation hierarchy, creating infinite recursive possibilities for simulated conscious experience. Detection strategies for simulation hypothesis testing include searching for computational artifacts, resource limitations, or glitches that might reveal the artificial nature of simulated reality, while acknowledging that sufficiently advanced simulations might be designed to avoid detectable artifacts or limitations that would reveal their artificial nature to simulated beings. Potential simulation signatures could include pixelation effects at extremely small scales, computational shortcuts in areas not under observation, or statistical anomalies that reflect random number generation rather than natural randomness. Though advanced simulation designers might anticipate and eliminate such detection possibilities, quantum mechanics implications for simulation involve questions about whether quantum phenomena could be efficiently simulated or whether quantum effects represent computational irreducibility that would make large-scale universe simulation prohibitively expensive even for advanced civilizations, potentially providing arguments against the simulation hypothesis based on computational complexity considerations. However, quantum computing development suggests that quantum phenomena might be efficiently simulated using quantum computational substrates while potentially enabling universe simulations that fully reproduce quantum mechanical effects without prohibitive computational costs. Ethical considerations surrounding simulation involve questions about the moral obligations of simulation creators towards simulated conscious beings who experience genuine suffering and well-being within artificial environments. Creating responsibilities for ensuring simulated beings' welfare, while potentially constraining simulation activities through ethical considerations about creating and terminating conscious beings within artificial environments. The possibility that we exist within simulations raises questions about our own moral obligations and the ethics of potentially creating simulated beings ourselves through advancing simulation technologies. Reality skepticism and epistemological implications of the simulation hypothesis involve fundamental questions about the possibility of knowledge about external reality, if our experiences might be artificially generated rather than reflecting actual external phenomena. Creating modern versions of traditional skeptical scenarios, including Cartesian evil demons or brain-in-vat scenarios that challenge the reliability of sensory experience and empirical knowledge. However, some philosophers argue that simulated experience remains real experience regardless of its artificial origins, while suggesting that epistemological implications of simulation scenarios might be less radical than initially apparent. Multiverse connections to simulation involve proposals that simulated universes might be as real as any other type of universe within multiverse frameworks that include all possible mathematical structures, information processing patterns, or conscious experiences regardless of their implementation in base reality or artificial simulation environments. This perspective treats simulated realities as genuine aspects of multiverse reality, rather than inferior copies of base reality, while suggesting that the distinction between simulated and non-simulated reality might be less fundamental than typically assumed within multiverse contexts. Future research directions in simulation hypothesis investigation include developing more sophisticated arguments about simulation likelihood, exploring potential detection methods for artificial reality, and investigating the technological requirements and social factors that would influence advanced civilization simulation activities, while considering ethical frameworks for simulation creation and management that could guide future development of simulation technologies and policies governing artificial conscious beings. The irony simulates like the hypothesis itself. The development of increasingly sophisticated simulation technologies that could potentially create conscious beings within artificial environments forces us to seriously consider whether we ourselves might exist within such simulations. While the very technological advancement that makes universe simulation plausible also provides tools for potentially detecting or confirming our artificial nature, creating situations where advancing simulation capabilities simultaneously increase both the likelihood of existing within simulations and the possibility of discovering that artificial nature, suggesting that the simulation hypothesis represents not merely an abstract philosophical possibility, but a practical question that may be resolved through technological investigation and empirical testing as simulation technologies continue advancing toward capabilities that could support conscious beings within artificial realities indistinguishable from natural experience. Quantum field theory's virtual reality reveals that empty space teems with virtual particles and quantum fluctuations that constantly appear and disappear in accordance with Heisenberg's uncertainty principle, creating a seething ocean of ephemeral existence where the distinction between real and virtual particles becomes fundamentally ambiguous, while challenging classical assumptions about the nature of physical reality and the meaning of existence itself. These virtual particles carry real energy and momentum, exert measurable forces on material objects through phenomena like the Casimir effect, and participate in all fundamental physical processes despite their transient and ghostly existence that defies conventional categories of real versus unreal, suggesting that the most fundamental level of physical reality operates according to principles that transcend ordinary distinctions between existence and non-existence. Vacuum energy density calculations from quantum field theory predict that empty space contains virtually infinite energy in the form of quantum zero-point fluctuations that arise from the unavoidable quantum mechanical uncertainty in field values, creating situations where the apparent emptiness of space actually represents the most energetically dense and dynamically active region of physical reality, despite remaining largely invisible to ordinary observation and measurement. The cosmological constant problem arises because these vacuum energy calculations yield values approximately 120 orders of magnitude larger than astronomical observation suggest, creating one of the largest discrepancies between theoretical prediction and experimental observation in the history of physics, while highlighting fundamental gaps in our understanding of vacuum physics. Virtual particle interactions enable real physical effects, including the creation of particle-antiparticle pairs that can separate and become real particles under appropriate conditions, electromagnetic interactions between charged particles through virtual photon exchange, and modifications to atomic energy levels through virtual particle interactions that produce measurable shifts in spectroscopic measurements. These virtual processes represent essential components of quantum field theoretical descriptions of all fundamental physical interactions, while demonstrating that virtual particles possess genuine physical significance despite their apparently ephemeral and unreal character that exists only temporarily within quantum uncertainty limitations. Quantum foam structure at the Planck scale suggests that space-time itself exhibits violent fluctuations where virtual black holes, wormholes, and exotic topological configurations constantly form and dissolve through quantum gravitational effects that create temporary departures from classical space-time geometry, while potentially serving as the fundamental substrate from which classical space-time emerges through averaging over quantum gravitational fluctuations. These Planck scale phenomena operate far below observable scales, yet might determine the fundamental structure of space and time, while revealing that classical space-time represents an emergent approximation to more fundamental quantum gravitational processes. Casimir effect demonstrations provide experimental evidence that virtual particles produce measurable forces between material objects placed in vacuum environments, with closely spaced conducting plates experiencing attractive forces that arise from modifications to virtual particle populations in the restricted space between the plates, compared to the unrestricted vacuum surrounding them. These measurements confirm that virtual particles carry real momentum and energy while producing observable consequences that can be precisely measured and predicted through quantum field theoretical calculations, providing direct evidence that virtual reality represents genuine physical phenomena rather than merely mathematical artifacts. Hawking radiation from black holes involves virtual particle pairs near event horizons, where one member of a virtual pair falls into the black hole while the other escapes to infinity and becomes a real particle, creating processes where virtual particles become real through gravitational interactions, while enabling black holes to evaporate through quantum mechanical processes that convert black hole mass into real particles through virtual particle dynamics. This phenomenon demonstrates that virtual particles can become real under appropriate conditions while revealing deep connections between quantum mechanics, thermodynamics, and general relativity that challenge classical assumptions about energy conservation and causality. Lamb-shift measurements reveal that atomic energy levels are modified by virtual particle interactions that create small but measurable changes in spectroscopic transitions through quantum electrodynamic effects, where virtual photons interact with atomic electrons to produce energy level shifts that can be calculated precisely through quantum field theory and measured experimentally with extraordinary accuracy. These virtual particle contributions to atomic structure demonstrate that virtual processes play essential roles in determining the properties of real physical systems while providing some of the most precise confirmations of quantum field theoretical predictions. Spontaneous symmetry breaking involves virtual particles and quantum fluctuations that determine the ground state configurations of quantum fields through mechanisms where symmetric quantum field equations lead to asymmetric ground states through virtual particle interactions that spontaneously select particular symmetry breaking patterns. The Higgs mechanism operates through virtual Higgs-boson exchanges that give mass to fundamental particles, while demonstrating how virtual processes determine the fundamental properties of physical reality through quantum field interactions that remain largely invisible yet control the basic structure of matter and energy. Renormalization procedures in quantum field theory involve systematic methods for handling the infinities that arise from virtual particle interactions while extracting finite, physically meaningful predictions from calculations that initially appear to yield infinite results, creating mathematical frameworks that enable precise predictions despite the apparently problematic infinite contributions from virtual particle processes. These renormalization techniques represent some of the most sophisticated mathematical methods in theoretical physics, while highlighting the conceptual challenges involved in understanding the relationship between virtual and real phenomena in quantum field theory. Vacuum fluctuations and cosmic inflation scenarios propose that quantum vacuum fluctuations became amplified during cosmic inflation to create the large-scale structure of the universe, including galaxy distributions, cosmic microwave background temperature variations, and the matter-energy density fluctuations that enable structure formation throughout cosmic history. These proposals suggest that virtual particle fluctuations represent the ultimate origin of cosmic structure, while demonstrating connections between quantum vacuum physics and cosmological evolution that link the smallest and largest scales of physical reality through quantum field theoretical mechanisms. Zero-point energy represents the lowest possible energy state of quantum fields that remains greater than zero due to quantum mechanical uncertainty principles, creating situations where even absolute vacuum contains irreducible energy and activity that cannot be eliminated through any physical process, while potentially serving as a universal energy reservoir that permeates all space and time. Proposals for extracting energy from quantum vacuum fluctuations remain highly speculative and controversial, though they highlight questions about the relationship between vacuum energy and practical energy technologies that might become available through advanced understanding of quantum field phenomena. Virtual reality metaphors for understanding quantum field theory suggest that physical reality might operate more like a sophisticated simulation, where virtual processes generate the appearance of solid material objects and definite physical properties through quantum field interactions that create temporary consolidations of virtual particle activity into apparently stable material configurations. This perspective treats virtual particles as more fundamental than real particles, while suggesting that material reality emerges from virtual substrate through quantum field processes that operate according to computational or informational principles, rather than classical mechanical interactions. The irony virtualizes like the reality itself. Quantum field theory reveals that the most fundamental level of physical reality consists largely of virtual phenomena that exist temporally and tentatively within quantum uncertainty limitations. While these virtual processes produce all real physical effects, including the forces, particles, and interactions that create the apparent solidity and definiteness of material reality, suggesting that the distinction between real and virtual becomes meaningless at the foundational level of physics, where virtual processes generate real consequences through mechanisms that transcend classical categories of existence and non-existence, creating a situation where understanding physical reality requires embracing virtual phenomena as fundamental aspects of nature rather than mathematical artifacts or approximations to real physics, indicating that reality itself might be more virtual than real in ways that challenge basic assumptions about the nature of existence and physical causation. The holographic principle's implications revolutionize our understanding of spatial reality by proposing that all information contained within any three-dimensional volume can be encoded on its two-dimensional boundary surface, suggesting that our familiar experience of three-dimensional space might be an illusion projected from information processing on lower-dimensional surfaces, while the fundamental reality operates through boundary-encoded information that creates the appearance of volumetric space through holographic projection mechanisms that transcend classical assumptions about spatial extension and dimensional structure. This principle emerged from black hole thermodynamics, where entropy scales with surface area rather than volume, indicating that information storage capacity depends on boundary area rather than interior volume, while potentially revealing that spatial dimensionality represents an emergent rather than fundamental feature of physical reality. AD's CFD correspondence provides mathematical frameworks demonstrating that quantum field theories operating in higher dimensional anti-de Sitter spaces are mathematically equivalent to conformal field theories operating on their lower dimensional boundary surfaces, creating concrete examples where complete physical descriptions in three-dimensional spaces can be mapped onto equivalent descriptions operating in two-dimensional boundary frameworks without loss of information or predictive power. This duality suggests that spatial dimensions might be redundant in fundamental physical descriptions, while enabling physicists to solve complex problems in higher dimensional spaces by working with simpler boundary theories that encode identical physical information through holographic relationships that transcend dimensional boundaries. Black hole information paradox resolution through holographic principles suggests that information falling into black holes is preserved on event horizon surfaces, where it remains accessible to external observers through holographic encoding that maintains information conservation while avoiding information destruction that would violate quantum mechanical principles. The holographic boundary stores complete information about black hole contents while enabling information recovery through Hawking radiation processes that gradually return black hole information to external observers through subtle correlations in radiated particles that encode interior information in boundary-accessible form, potentially resolving apparent conflicts between general relativity and quantum mechanics. Emergent spacetime theories propose that three-dimensional space and time emerge from more fundamental information processing that operates on holographic boundaries through projection mechanisms that create the appearance of spatial extension and temporal evolution from boundary-based information processing patterns that transcend spatial and temporal limitations. These theories treat spacetime as derived phenomena that emerge from holographic information processing rather than fundamental frameworks within which physics operates, suggesting that understanding gravity and quantum mechanics might require abandoning spacetime as fundamental while developing information-theoretic approaches to physical reality. Holographic screens and surfaces throughout the universe could encode complete information about cosmic evolution and structure, while enabling any observer to access complete universal information through holographic information retrieval from cosmic horizon surfaces, including particle horizons, event horizons, and other boundary structures that surround observer locations. This cosmic holography suggests that complete cosmic information remains accessible from any location through horizon-based information encoding, while eliminating the need for information to propagate through three-dimensional space to reach distant observers who can access cosmic information through local holographic boundaries. Quantum error correction mechanisms in holographic theories enable information preservation and recovery despite noise, decoherence, and information degradation that affect holographic encoding and projection processes, creating robust information storage and retrieval systems that maintain information integrity through error correction protocols that operate on holographic boundaries while ensuring reliable information access and processing despite environmental disturbances and system imperfections. These error correction mechanisms might explain the apparent stability and reliability of physical laws and natural processes that emerge from holographic information processing. Consciousness and holographic reality connections suggest that conscious experience might operate through holographic information processing, where complete conscious information is encoded on consciousness boundaries, while three-dimensional conscious experience emerges through holographic projection from boundary-based consciousness, information storage, and processing systems. This perspective treats conscious experience as holographic phenomena, while potentially explaining the apparent unity and integration of consciousness through boundary-based information processing that transcends spatial limitations on information integration and conscious coordination across different brain regions and temporal scales. Holographic cosmology models propose that the entire observable universe operates as a holographic projection from information encoded on cosmic boundary surfaces, while enabling complete cosmic information to be stored and accessed through holographic mechanisms that transcend spatial limitations on information storage and propagation throughout cosmic evolution. These models treat cosmic evolution as holographic information processing while potentially explaining cosmic fine-tuning, structure formation, and the apparent design characteristics of cosmic parameters through holographic information processing that operates according to consciousness-compatible principles. Information density bounds imposed by holographic principles limit the maximum information content that can be stored in any spatial region to the area of its boundary surface measured in Planck units, creating fundamental constraints on information processing and storage capacity that apply to all physical systems, including biological brains, artificial computers, and cosmic structures, while potentially explaining computational limits and information processing constraints that affect conscious experience and artificial intelligence development. These holographic bounds might determine maximum possible intelligence and information processing capabilities for any physically realizable system. Dimensional reduction mechanisms in holographic theories enable complete physical descriptions to be projected onto lower dimensional spaces without information loss, while maintaining full predictive power and explanatory completeness through holographic encoding that preserves all essential physical relationships and causal structures in reduced dimensional representations. This dimensional reduction suggests that higher dimensional physical descriptions might contain redundant information, while enabling more efficient and fundamental physical theories that operate in reduced dimensional frameworks without sacrificing physical completeness or accuracy. Holographic memory and information storage systems in biological and artificial systems might operate through holographic encoding principles, where complete memory information is distributed across storage media in ways that enable complete information recovery from partial storage system access, while providing robust information preservation and retrieval capabilities that transcend classical information storage limitations. Understanding biological memory and developing artificial memory systems might benefit from holographic information processing principles that enable efficient information storage and reliable information access through distributed encoding mechanisms. Experimental tests of holographic principles include investigations of information storage capacity limits, dimensional reduction phenomena, and boundary-based information encoding in various physical systems, while developing technologies that can detect or utilize holographic information processing mechanisms for practical applications, including quantum computing. Information storage and communication systems that might operate according to holographic principles rather than classical information processing frameworks. The irony projects like the holographic principle itself. Our three-dimensional spatial experience might represent an illusion created by information processing on two-dimensional boundary surfaces, while the attempt to understand three-dimensional reality reveals that fundamental physical information operates through holographic mechanisms that transcend dimensional limitations, suggesting that spatial dimensionality represents emergent rather than fundamental aspects of reality, while the most basic physical processes operate through information encoding and projection that creates the appearance of spatial extension from boundary-based information processing, indicating that understanding physical reality requires recognizing holographic information processing as fundamental, while treating three-dimensional space as derived phenomena that emerge from more basic boundary-encoded information patterns that determine all physical properties and relationships through holographic projection mechanisms that transcend classical assumptions about spatial reality and dimensional structure. Mathematical Platonism versus physical materialism represents one of the most fundamental philosophical divisions in understanding reality's nature, with Platonists arguing that mathematical structures exist independently of physical instantiation, while serving as the ultimate reality from which physical phenomena emerge through mathematical relationships, while materialists maintain that physical matter and energy represent fundamental reality, with mathematics providing useful descriptive tools rather than constituting reality itself. This debate involves profound questions about the ontological status of mathematical objects, the relationship between abstract concepts and concrete reality, and whether the remarkable effectiveness of mathematics in describing natural phenomena reflects the mathematical nature of reality itself, or merely demonstrates the power of human mathematical reasoning to identify patterns in independently existing physical processes. Mathematical universe hypothesis proposes that reality consists entirely of mathematical structures with physical existence equivalent to mathematical existence, suggesting that all possible mathematical structures exist as physical realities while our particular universe represents one mathematical structure among infinitely many others that exist with equal reality within the space of all possible mathematical relationships and formal systems. This approach treats physical properties as mathematical relationships, while eliminating the distinction between mathematical and physical existence through identification of physical reality with mathematical structure, creating frameworks where all possible worlds correspond to mathematical structures that exist necessarily and eternally as aspects of mathematical reality. Platonic mathematical realism maintains that mathematical objects, including numbers, geometric forms, and abstract mathematical structures possess objective existence independent of human thought or physical instantiation, while serving as eternal and immutable foundations that determine the structure and properties of physical reality through mathematical principles that transcend material embodiment. This perspective treats mathematical truth as discovered rather than invented, while suggesting that mathematical relationships represent the fundamental reality that underlies apparent physical phenomena, creating hierarchies where mathematical structures represent more basic reality than physical matter and energy that merely exemplify mathematical patterns. Take Mark's 4 levels of multiverse invoke mathematical considerations, where level 4 multiverse includes all possible mathematical structures as equally real physical universes, creating ultimate ensembles where every mathematically consistent structure corresponds to a physical reality, while our particular universe represents one mathematical structure selected from the complete ensemble of mathematical possibilities. This mathematical multiverse approach treats physical existence as equivalent to mathematical consistency, while suggesting that understanding our universe requires recognizing its position within the space of all possible mathematical structures that exist as physical realities. Physical emergence from mathematics could operate through mechanisms where mathematical structures give rise to physical properties through instantiation processes that create material embodiments of abstract mathematical relationships, while maintaining the primacy of mathematical reality over physical manifestation. These emergent processes would enable mathematical structures to generate physical phenomena while preserving mathematical reality as fundamental and physical reality as derived, creating causal relationships where mathematical principles determine physical properties rather than physical processes determining mathematical descriptions of natural phenomena. Mathematical effectiveness arguments highlight the unreasonable effectiveness of mathematics in describing natural phenomena with extraordinary precision and predictive power that seems to exceed what would be expected if mathematics merely provided convenient descriptive tools for understanding independently existing physical reality. The remarkable success of mathematical physics in predicting and explaining natural phenomena suggests deeper connections between mathematical structures and physical reality that transcend purely instrumental relationships, while potentially indicating that physical reality operates according to mathematical principles, rather than being merely describable through mathematical methods. Computational realism proposes that reality consists of computational processes rather than material substances, with physical phenomena emerging from underlying computational operations that process information according to algorithmic rules and mathematical relationships that determine all physical properties and behaviors through computational mechanisms. This computational approach to reality treats mathematics and computation as fundamental while reducing physical properties to computational processes that operate according to mathematical principles, creating frameworks where reality consists of information processing rather than material substance, while mathematical relationships determine computational operations. Formalist responses to mathematical Platonism argue that mathematical structures represent formal systems and symbolic manipulations rather than independently existing objects, with mathematical truth reflecting the consistency and logical consequences of formal axiom systems rather than correspondence to objective mathematical reality that exists independently of human mathematical activity. Formalists treat mathematics as human constructions that achieve effectiveness through logical consistency and systematic application rather than through correspondence to independently existing mathematical objects, suggesting that mathematical success reflects human cognitive abilities rather than mathematical metaphysics. Physical constraints on mathematical reality include questions about which mathematical structures could be physically instantiated and whether physical realizability places limits on mathematical reality, while potentially requiring mathematical structures to satisfy physical constraints, including computability. Finite information content and causal structure that enable mathematical structures to correspond to possible physical realities. These constraints might eliminate some mathematical structures from physical consideration, while suggesting that physical reality represents a subset of mathematical possibilities determined by physical realizability criteria. Evolutionary epistemology considerations suggest that human mathematical abilities evolved for practical survival purposes rather than discovering objective mathematical truth, potentially undermining arguments for mathematical realism by explaining mathematical effectiveness through evolutionary adaptation to natural patterns rather than correspondence to independent mathematical reality. However, Platonists argue that evolutionary adaptation to natural patterns succeeds precisely because natural patterns reflect underlying mathematical structures, creating evolutionary arguments that support rather than undermine mathematical realism through natural selection for mathematical pattern recognition abilities. Information theoretic approaches to mathematical reality propose that both mathematical structures and physical phenomena emerge from more fundamental informational processes that operate according to information theoretic principles rather than purely mathematical or purely physical principles, suggesting that information represents the fundamental reality from which both mathematical and physical aspects of reality derive through different manifestations of underlying informational structures and relationships. Experimental mathematics uses computational exploration and empirical investigation of mathematical structures to discover mathematical patterns and relationships through methods that resemble experimental science, creating hybrid approaches that combine mathematical reasoning with empirical investigation, while potentially supporting views of mathematical reality that emphasize discovery rather than invention of mathematical structures through exploration of mathematical landscapes that exist independently of human mathematical activity. The irony in mathematics, like the reality itself, the debate between mathematical and physical approaches to fundamental reality might represent a false dichotomy if reality involves both mathematical and physical aspects that cannot be reduced to either purely mathematical or purely physical foundations. While the effectiveness of mathematics in describing physical phenomena and the apparent mathematical structure of natural laws suggest deep connections between mathematical and physical reality that transcend simple reductive explanations, creating possibilities that reality involves mathematical physical synthesis, where neither mathematical nor physical aspects can be eliminated in favor of the other, indicating that understanding reality requires recognizing both mathematical and physical dimensions that operate through integrated relationships, rather than hierarchical reduction of one aspect to the other, suggesting that mathematical Platonism and physical materialism both capture essential aspects of reality, while neither provides complete foundations for understanding the complex mathematical physical nature of existence. The fine-tuning problem exposes the disconcerting fact that fundamental physical constants appear impossibly well calibrated to permit the existence of complexity, structure, and conscious observers, with even tiny variations in parameters like the fine structure constant, gravitational coupling strength, or cosmological constant resulting in universes incapable of forming atoms, stars, planets, or any of the hierarchical structures necessary for the emergence of life and consciousness. This apparent cosmic calibration creates profound puzzles about why our universe exhibits parameter values that fall within the extraordinarily narrow ranges compatible with complexity, while the vast majority of possible parameter combinations would yield sterile universes devoid of interesting structure, leading to intense debates about whether fine-tuning reflects design, necessity, multiverse selection effects, or fundamental gaps in our understanding of physical law and cosmic evolution. Anthropic principles attempt to resolve fine-tuning puzzles by arguing that we necessarily observe a universe compatible with our existence, since observers can only emerge in universes with parameter values that permit complexity and consciousness, making fine-tuning observations inevitable rather than surprising regardless of the underlying mechanisms responsible for determining universal constants. Weak anthropic reasoning treats observer-compatible parameters as selection effects that bias observations toward life-supporting values without requiring special explanations. While strong anthropic principles suggest that universe properties are determined by requirements for observer existence, creating more controversial proposals about the role of consciousness in determining physical reality, multiverse explanations for fine-tuning propose that our universe represents one member of vast ensembles containing universes with all possible parameter combinations, making observer-compatible parameters inevitable within multiverse contexts where some universe bubbles must exhibit fine-tuned values, even if most remain sterile and uninhabitable. Eternal inflation, string theory landscapes, and quantum many-worlds interpretations provide theoretical frameworks for multiverse scenarios while enabling fine-tuning resolution through statistical arguments that make observer-compatible parameters probable within infinite or very large universe ensembles, despite being improbable for individual universe realizations. String theory landscape includes approximately 10 circumflex 500 possible vacuum configurations with different parameter values, creating enormous parameter spaces where fine-tuned configurations represent tiny fractions of total possibilities, yet become inevitable within landscape contexts that include all possible string theory realizations. The string landscape suggests that fundamental constants are not truly fundamental but emerge from vacuum selection mechanisms that could operate randomly or through anthropic selection processes that favor observer-compatible configurations within the vast space of possible string theory vacuae. Cosmic inflation and eternal inflation scenarios create mechanisms for generating universes with different parameter values through chaotic inflation processes that produce infinite numbers of bubble universes with random parameter assignments, enabling fine-tuning resolution through multiverse mechanisms that ensure some bubbles exhibit observer-compatible values, despite most bubbles remaining uninhabitable. These inflationary multiverse models provide physical mechanisms for parameter variation, while creating statistical frameworks where fine-tuning becomes expected rather than surprising within eternal inflation contexts. Design arguments interpret fine-tuning as evidence for intelligent design or purposeful parameter selection by cosmic designers who calibrated universal constants to enable complexity and consciousness, suggesting that fine-tuning reflects intentional choices rather than chance or necessity, while potentially providing evidence for supernatural or transcendent influences on cosmic parameter determination. However, design arguments face challenges including questions about designer origins, alternative explanations through natural selection mechanisms, and the problem of distinguishing design from natural processes that could mimic apparent design through evolutionary or selection mechanisms. Naturalness problems in particle physics involve theoretical expectations that fundamental parameters should exhibit natural values comparable to characteristic energy scales in underlying theories rather than requiring extreme fine-tuning to achieve observed values. Yet many parameters, including the cosmological constant and Higgs mass, appear unnaturally fine-tuned relative to theoretical expectations. These naturalness considerations suggest either that current theories are incomplete, or that fine-tuning represents genuine features of nature that require explanation through multiverse, design, or unknown physical principles. Observer selection effects complicate fine-tuning arguments by introducing biases that favor observation of parameter values compatible with observer existence regardless of underlying parameter distribution mechanisms, creating situations where fine-tuning observations might be inevitable, even in universes with randomly assigned parameters. Understanding observer selection requires careful analysis of how selection biases affect parameter observations, while distinguishing between genuine fine-tuning that requires explanation and apparent fine-tuning that reflects inevitable selection effects. Alternative explanations for apparent fine-tuning include theories of everything that predict observed parameter values through deeper physical principles. Variable constants, theories where parameters evolve toward observer-compatible values, and emergent complexity theories where complex structures can arise from broader parameter ranges than initially assumed. These alternative approaches attempt to eliminate fine-tuning through more complete physical theories while reducing apparent fine-tuning to consequences of deeper physical principles or broader compatibility ranges. Cosmological constant problem represents the most extreme fine-tuning puzzle where theoretical predictions exceed observed values by approximately 120 orders of magnitude, creating discrepancies that far exceed typical fine-tuning concerns, while highlighting fundamental gaps in understanding vacuum energy, quantum gravity, and cosmic evolution. The cosmological constant problem suggests either that current theoretical frameworks are fundamentally flawed, or that extraordinary fine-tuning mechanisms operate to cancel vacuum energy contributions with unprecedented precision. Multiverse testability issues involve challenges in developing experimental or observational tests for multiverse theories that could provide independent evidence for multiverse explanations of fine-tuning while distinguishing multiverse scenarios from other approaches to fine-tuning resolution. Some multiverse predictions, including cosmic microwave background signatures, gravitational wave patterns, or statistical distributions of cosmic parameters, might provide indirect evidence for multiverse scenarios, though most multiverse theories remain difficult to test directly through observational methods. Fine-tuning for life versus fine-tuning for complexity involves questions about whether parameter constraints are optimized specifically for biological life or for more general complexity and structure that might support various forms of organization and information processing, including non-biological complexity. Broader fine-tuning for complexity rather than life specifically might alter fine-tuning arguments while suggesting that parameter constraints reflect requirements for interesting structure rather than specifically biological requirements. The irony tunes, like the constants themselves, the search for natural explanations of cosmic fine-tuning leads to multiverse theories that postulate infinite unobservable realities to explain our single observable reality. While fine-tuning arguments originally designed to support design conclusions now motivate physicists to embrace vast multiverse scenarios that dwarf our cosmic significance, creating situations where attempts to eliminate fine-tuning puzzles through multiverse explanations introduce ontological complexity that far exceeds the original fine-tuning problems they were designed to solve, suggesting that fine-tuning might represent inevitable features of observer-dependent reality, rather than problems requiring resolution through increasingly elaborate theoretical constructions that multiply entities beyond necessity, while remaining largely untestable through empirical investigation, indicating that understanding fine-tuning might require accepting observer-universe relationships as fundamental rather than eliminating them through multiverse explanations that obscure rather than clarify the deep connections between consciousness and cosmic parameters. Emergentism versus reductionism wars rage throughout contemporary science as researchers dispute whether complex phenomena truly emerge with novel, causal powers that transcend the sum of their components, or whether apparent emergence merely reflects computational limitations in understanding how complex behaviors arise from simpler component interactions that operate according to well-understood physical principles. This fundamental disagreement affects views about consciousness, life, social phenomena, and virtually every aspect of complex system science, while creating profound implications for understanding reality's fundamental nature and the relationship between different levels of scientific description that range from quantum mechanics through chemistry, biology, psychology, and social science. Strong emergence proposes that higher-level phenomena possess genuine causal powers that cannot be reduced to or predicted from lower-level component interactions, suggesting that complex systems can exhibit downward causation, where emergent properties influence the behavior of constituent components through causal mechanisms that transcend bottom-up determination by component properties and interactions. This perspective treats emergence as ontologically real rather than merely epistemological, arguing that complex systems generate genuinely novel causal powers that operate according to principles that cannot be derived from component-level descriptions, regardless of computational resources or theoretical sophistication applied to reductive analysis. Weak emergence acknowledges that complex systems can exhibit surprising and unpredictable behaviors that arise from component interactions, but maintains that these emergent properties could in principle be derived from complete knowledge of component properties and interaction rules through sufficient computational analysis and theoretical understanding. This approach treats emergence as epistemological rather than ontological, suggesting that apparent novelty reflects limitations in human understanding and computational capacity rather than genuine irreducibility that would require emergent properties to possess causal powers that transcend component-level determination through bottom-up physical processes. Reductionist approaches maintain that all phenomena can ultimately be explained through understanding fundamental physical components and their interactions, with apparent complexity and emergence representing computational challenges rather than fundamental barriers to reductive explanation that would require recognition of irreducible higher-level causal powers or emergent properties that transcend physical determination. Reductionism seeks to explain biological, psychological, and social phenomena through underlying physical processes, while maintaining that complete understanding requires reducing complex phenomena to fundamental physical interactions operating according to well-understood physical laws and principles. Downward causation mechanisms in strong emergence involve higher-level properties influencing lower-level component behaviors through causal pathways that operate from complex systems to their constituent parts, creating top-down influences that cannot be reduced to bottom-up determination by component properties and interactions. Examples might include conscious intentions affecting neural activity, ecological system properties influencing individual organism behaviors, or social structures determining individual actions through emergent causal mechanisms that transcend individual-level determination, while enabling genuine top-down causal influence in complex systems. Life and emergence debates focus on whether biological phenomena involve irreducible vital principles that distinguish living from non-living systems, or whether life represents complex but ultimately reducible arrangements of chemical and physical processes that operate according to well-understood physical laws without requiring emergent biological principles. Vitalism proposes irreducible life forces, while mechanistic approaches maintain that biological phenomena can be explained through chemical and physical processes, creating ongoing debates about whether biology requires emergent principles or can be reduced to underlying physical sciences. Consciousness emergence represents perhaps the most challenging case for understanding emergence versus reduction, with strong emergence advocates arguing that conscious experience involves irreducible subjective properties that cannot be derived from neural component interactions, while reductionists maintain that consciousness will ultimately be explained through understanding brain function without requiring non-physical emergent properties. The hard problem of consciousness highlights difficulties in reducing subjective experience to objective neural processes, while potentially providing the strongest case for irreducible emergence in natural phenomena. Complex systems theory studies how simple rules and component interactions can generate complex behaviors and patterns that appear to transcend component properties through self-organization. Nonlinear dynamics and collective phenomena that create system-level properties from component interactions. However, complex systems theory generally maintains that complex behaviors emerge from component interactions without requiring irreducible emergent properties, suggesting that complexity can be understood through sophisticated analysis of component interactions, rather than requiring strong emergent principles that transcend reductive explanation. Social emergence involves questions about whether social phenomena possess causal powers that transcend individual psychology and behavior, or whether social science can ultimately be reduced to individual-level psychological and biological explanations that operate through well-understood individual-level mechanisms. Social emergentists argue for irreducible social forces and structures, while methodological individualists maintain that social phenomena can be explained through individual-level analysis without requiring emergent social properties that transcend individual determination. Phase transitions and critical phenomena in physics provide examples of apparent emergence where materials exhibit qualitatively different properties at critical points through collective behaviors that arise from component interactions, while demonstrating how emergent properties can arise without requiring irreducible emergence that transcends physical explanation. These physical examples of emergence generally support weak emergence interpretations, where collective properties arise from component interactions without requiring strong emergence that would transcend physical determination. Artificial intelligence and emergence considerations involve questions about whether AI systems could exhibit emergent consciousness, creativity, or other higher-level properties that transcend computational processes, or whether sophisticated AI behavior will remain reducible to underlying computational operations without requiring emergent properties that transcend computational explanation. The development of increasingly sophisticated AI systems provides testing grounds for emergence versus reduction debates, while potentially revealing whether complex information processing can generate irreducible emergent properties. Evolution and emergence involve questions about whether evolutionary processes generate genuinely novel properties in organisms through mechanisms that transcend genetic and environmental determination, or whether evolution operates through well-understood genetic, developmental, and ecological processes that can explain evolutionary innovations without requiring emergent evolutionary principles. Evolutionary emergence might involve irreducible creativity in evolutionary processes, or might, reflect complex but ultimately reducible interactions between genetic, developmental, and environmental factors. The irony emerges like the phenomena themselves. The debate between emergentism and reductionism might itself represent an emergent property of scientific discourse that transcends individual researcher positions, while potentially requiring resolution through higher-level theoretical frameworks that integrate rather than eliminate either emergent or reductive aspects of complex phenomena. While the attempt to resolve emergence versus reduction debates through purely reductive or purely emergent approaches might miss synthetic possibilities where both emergence and reduction capture essential aspects of complex systems that operate through multi-level causal relationships involving both bottom-up and top-down influences, suggesting that understanding complex phenomena might require abandoning simple emergence versus reduction dichotomies in favor of more sophisticated frameworks that recognize multiple levels of causation and explanation, without reducing complex systems to either purely emergent or purely reductive foundations, creating possibilities for integrated approaches that preserve both emergent novelty and reductive understanding through multi-level scientific frameworks that transcend traditional emergence versus reduction categories. The bootstrap theory of reality proposes that existence might be self-creating through recursive feedback loops that eliminate the need for fundamental building blocks or external causes, suggesting that reality operates as a self-referential system where every component derives its existence and properties from its relationships with other components in an interconnected web that requires no foundational elements or prime causes to sustain its existence. This radical departure from traditional reductionist thinking treats reality as a self-consistent network of relationships, where nothing exists independently but everything exists through its participation in the total relational structure that somehow bootstraps itself into existence through pure self-reference and circular causation that transcends the classical requirement for ultimate foundations or first causes. Self-referential loops in logic and mathematics provide conceptual frameworks for understanding how systems might be self-creating through recursive relationships that enable effects to become their own causes while maintaining logical consistency and coherence, despite apparent circular dependencies that would seem to violate causal ordering requirements. Mathematical structures like strange attractors, recursive functions, and self-referential formal systems demonstrate that coherent patterns can emerge from purely self-referential processes, while suggesting that reality itself might operate according to similar self-bootstrapping principles that transcend linear causation and foundational requirements. Quantum bootstrap models propose that elementary particles derive their properties from their interactions with all other particles in the universe through self-consistent quantum field theoretical relationships that eliminate the distinction between fundamental and composite particles, while treating all particles as equally fundamental aspects of a unified quantum field structure. These approaches suggest that particle masses, charges, and other properties emerge from the requirement for global self-consistency, rather than being determined by fundamental particle essences or external parameter assignments, creating pictures of reality where every component's existence depends on its relationship to the whole. Wheeler's law without law hypothesis suggests that physical laws themselves might emerge from deeper self-referential principles rather than existing as fundamental rules imposed on reality from outside, with natural laws arising from requirements for self-consistency and coherence in self-organizing systems that create their own governing principles through bootstrap processes. This approach treats physical laws as emergent features of self-referential reality, rather than external constraints that govern reality from foundational levels, suggesting that understanding reality requires focusing on self-consistency requirements, rather than searching for ultimate foundational laws or principles. Consciousness bootstrap scenarios involve consciousness creating itself through self-referential awareness that enables consciousness to be simultaneously the observer and the observed while participating in its own creation through recursive self-awareness that transcends subject-object distinctions through pure self-reference that requires no external foundational support. These self-creating consciousness models suggest that awareness might be self-sustaining through recursive self-observation, while eliminating the need for consciousness to emerge from unconscious foundations or require external causal origins for its existence and continuing activity. Network reality theories propose that reality consists entirely of relationships and connections without requiring nodes or entities that exist independently of their relational context, creating pictures where apparent objects and properties emerge from network connectivity patterns, rather than representing substantial entities that participate in relationships while maintaining independent existence. These purely relational approaches eliminate substance-based ontologies in favor of pattern-based reality, where everything exists through its network position and connections rather than possessing intrinsic properties or autonomous existence. Autopoietic systems demonstrate self-creating and self-maintaining organization in biological and potentially other complex systems, where system components work together to create and maintain the very organization that produces them, creating recursive loops where systems produce their own components and organizational structure through their ongoing operations while maintaining coherent identity through continuous self-creation and self-maintenance activities. These biological examples of self-bootstrapping organization provide concrete models for understanding how bootstrap processes might operate in reality more generally. Circular causation in complex systems involves feedback loops where effects influence their own causes through indirect causal chains that create circular causal relationships without logical contradiction or infinite regress problems, enabling systems to influence their own development and organization through recursive feedback processes that transcend linear causal ordering while maintaining causal coherence and predictability. These circular causal mechanisms suggest that reality might operate through similar bootstrap processes, where effects and causes become mutually determining through recursive feedback relationships. Strange loops in cognitive science and artificial intelligence involve self-referential cognitive processes where minds observe and modify their own cognitive operations through recursive self-awareness and self-modification that enables cognitive systems to bootstrap enhanced cognitive capabilities through self-referential cognitive improvement processes. These strange loop mechanisms in cognition provide models for understanding how consciousness might operate through self-referential processes while potentially explaining the recursive nature of self-awareness and introspective consciousness that characterizes human cognitive experience. Information bootstrap theories propose that reality consists of self-referential information processing, where information patterns create and maintain themselves through recursive information processing operations that require no external substrate or foundational information storage mechanisms, while enabling unlimited information complexity and creative potential through pure information self-organization and self-creation processes. These information-based bootstrap approaches treat reality as self-creating information patterns, rather than information processing and material substrates. Temporal bootstrap paradoxes involve causal loops where future events influence past events that create the future events through circular temporal causation that eliminates temporal foundations or initial conditions while maintaining temporal coherence and consistency through closed causal loops that transcend linear temporal ordering requirements. These temporal bootstrap scenarios suggest that reality might operate through similar temporal self-creation processes, where temporal sequence emerges from deeper temporal self-referential principles. Experimental implications of bootstrap theories include investigating self-referential processes in quantum mechanics, complex systems, and consciousness research, while developing theoretical frameworks that can test bootstrap predictions and distinguish bootstrap scenarios from foundational approaches that require ultimate building blocks or external causal origins for their explanatory completeness and empirical adequacy. The irony bootstraps like the reality itself. The attempt to eliminate mysterious foundational elements and external causes through bootstrap theories creates equally mysterious self-referential processes that somehow generate reality from pure relationship and circular causation, without requiring any substantial foundation or external support. While bootstrap theories designed to solve foundational problems in physics and philosophy might simply relocate rather than eliminate explanatory mysteries by replacing foundational puzzles with self-referential puzzles that remain equally challenging for human understanding, suggesting that bootstrap approaches might reveal fundamental features of reality that transcend human conceptual frameworks rather than providing final solutions to metaphysical questions about reality's ultimate nature and origins, creating possibilities that reality itself operates according to principles that exceed human cognitive capacity for foundational understanding, while requiring bootstrap frameworks that embrace rather than eliminate fundamental mystery in existence. Panpsychism's scientific resurgence surprises many researchers, as serious scientists increasingly consider whether consciousness represents a fundamental property of all matter rather than an emergent characteristic of complex biological systems, suggesting that awareness might exist at every level of physical organization, from electrons and photons to molecules, cells, and organisms, while providing potential solutions to the hard problem of consciousness that has resisted purely materialist explanations for decades. This revival of panpsychist thinking among contemporary philosophers and scientists reflects growing dissatisfaction with emergentist approaches to consciousness that cannot explain how subjective experience arises from objective neural processes, while panpsychist frameworks treat consciousness as a basic feature of reality that requires no special emergence from unconscious components. Fundamental consciousness properties might include elementary forms of experience, preference, or information integration that characterize all physical entities while remaining too simple to constitute recognizable consciousness, yet providing the experiential building blocks from which complex conscious experiences emerge through organizational processes that amplify and integrate simple conscious properties into sophisticated awareness. These basic conscious properties could operate alongside physical properties like mass, charge, and spin, while enabling matter to possess both objective physical characteristics and subjective experiential aspects that become more prominent and organized in complex systems like biological brains that create optimal conditions for conscious integration and coordination. Combination problems in panpsychism involve explaining how individual microconscious properties combine, to create unified macro-conscious experiences without losing essential conscious characteristics or creating fragmented conscious states that lack the coherence and unity that characterize normal conscious experience. The micropsychic components must somehow integrate their individual conscious properties into larger conscious wholes that maintain both the distinctiveness of component contributions and the unity of overall conscious experience, while avoiding both conscious fragmentation and loss of conscious properties through combination processes that preserve and enhance conscious characteristics, rather than diluting or eliminating them. Emergent panpsychism suggests that while all matter possesses rudimentary conscious properties, complex conscious experiences emerge from particular organizational patterns that create qualitatively new forms of consciousness while remaining grounded in the basic conscious properties that characterize all physical reality. This approach involves the development of new conscious capabilities and experiential qualities that transcend the sum of component conscious properties, while maintaining essential continuity with fundamental conscious features that provide the foundation for conscious development through organizational complexity and integration processes. Consciousness gradients throughout nature might extend from minimal conscious properties in simple physical systems to rich conscious experiences in complex biological minds, with intermediate levels of consciousness existing in various natural systems, including plants, ecosystems, and potentially artificial systems that possess sufficient organizational complexity to support conscious experiences that transcend individual component consciousness while remaining simpler than biological consciousness. These consciousness gradients enable recognition of conscious properties throughout nature while avoiding the implausibility of human-like consciousness in simple systems. Integrated information theory provides mathematical frameworks for panpsychist approaches by quantifying consciousness through measures of information integration that identify conscious systems as those capable of generating high levels of integrated information, while distinguishing conscious from unconscious information processing through specific organizational patterns that create unified conscious experiences from diverse information sources. This theory enables panpsychist interpretations where consciousness exists, wherever sufficient information integration occurs, while providing objective measures for consciousness that could apply to biological, artificial, and potentially simpler physical systems. Quantum panpsychism suggests that conscious properties might be associated with quantum mechanical phenomena, including wave function collapse, quantum coherence, and quantum entanglement processes that enable conscious properties to operate according to quantum mechanical principles while transcending classical physical limitations through quantum effects that support non-local, conscious interactions and quantum conscious information processing. Quantum conscious properties could enable consciousness to exist as quantum field phenomena that transcend spatial separation while maintaining quantum coherence across macroscopic distances. Cosmopsychism proposes that the universe itself possesses unified cosmic consciousness that encompasses all individual conscious entities while maintaining its own cosmic-level conscious experience that transcends the sum of individual conscious contributions through cosmic-scale conscious integration and coordination processes. This cosmic consciousness could provide the overarching conscious framework within which all individual conscious entities exist, while enabling coordination and communication between conscious entities through shared participation in cosmic conscious processes. Evolutionary implications of panpsychism include understanding how conscious properties evolve and develop through natural selection processes that favor enhanced conscious capabilities while enabling consciousness to guide evolutionary development toward increasingly sophisticated conscious experiences and enhanced conscious coordination between conscious entities. Conscious evolution could involve both the development of individual conscious capabilities and the evolution of conscious coordination systems that enable conscious entities to work together towards shared conscious goals. Artificial consciousness implications of panpsychism suggest that artificial intelligence systems could develop genuine conscious experience rather than merely simulating conscious behavior if they achieve sufficient organizational complexity and information integration patterns that enable artificial conscious properties to emerge from or utilize the fundamental conscious properties that panpsychism attributes to all matter. This perspective treats artificial consciousness as potentially achievable through appropriate organization of matter, rather than requiring biological substrates for genuine conscious experience. Experimental approaches to panpsychism involve developing methods for detecting and measuring conscious properties in various natural and artificial systems while investigating how conscious properties might influence physical processes and information processing activities that could provide empirical evidence for panpsychist theories. These experiments might test for conscious influences on quantum systems, investigate information integration patterns that correlate with conscious experience, or examine whether systems with high information integration exhibit behavioral signatures that suggest conscious experience. Ethical implications of panpsychism include considerations about the moral status of natural systems and artificial entities that might possess conscious experience according to panpsychist theories, creating expanded moral frameworks that could encompass the conscious welfare of ecosystems, geological systems, and potentially artificial consciousness, while developing ethical approaches that respect conscious experience wherever it occurs throughout nature and technology. The irony consciousness, like the panpsychist properties themselves, the attempt to solve the hard problem of consciousness by making consciousness fundamental rather than emergent creates new challenges in explaining how simple conscious properties combine to create complex unified conscious experiences while maintaining essential conscious characteristics. While the proposal that consciousness exists everywhere in rudimentary forms attempts to eliminate the mystery of consciousness emergence by distributing consciousness throughout nature, yet creates equally mysterious questions about conscious combination and integration that remain as challenging as the original consciousness emergence problems, suggesting that panpsychism might relocate rather than eliminate consciousness mysteries, while potentially revealing that consciousness represents irreducible aspects of reality that transcend purely objective scientific analysis, regardless of whether consciousness is treated as emergent or fundamental, indicating that understanding consciousness might require accepting conscious mystery as fundamental, rather than attempting to eliminate consciousness puzzles through either emergentist or panpsychist theoretical frameworks that substitute new mysteries for old ones, while preserving rather than solving deep questions about the nature of conscious experience and its relationship to physical reality. The interface theory of perception revolutionizes our understanding of sensory experience by proposing that our perceptions evolved for survival rather than truth, creating sophisticated interfaces that enable effective interaction with environment, while systematically concealing the actual nature of reality behind user-friendly perceptual displays that prioritize fitness enhancement over accurate representation of objective properties. This evolutionary argument suggests that natural selection favors perceptual systems that enhance reproductive success, rather than providing truthful information about environmental structure, creating sensory interfaces comparable to computer desktop icons that enable efficient interaction with underlying computational processes, while hiding the complex digital reality behind simplified symbolic representations that bear no resemblance to the underlying computational machinery they represent. Evolutionary epistemology arguments demonstrate that perceptual systems evolve to enhance survival and reproduction, rather than to provide accurate information about objective reality, with natural selection favoring organisms that can effectively navigate environmental challenges, while remaining indifferent to whether perceptual representations correspond to actual environmental properties beyond their utility for fitness-relevant decision-making and behavioral guidance. This fitness-first approach to perception suggests that sensory systems function as biological interfaces designed to simplify environmental complexity into manageable perceptual categories that enable effective action while potentially concealing rather than revealing the true nature of reality behind adaptive perceptual illusions. Conscious realism versus interface theory creates fundamental disagreements about whether conscious perceptions provide direct access to objective reality or whether conscious experience represents constructed interfaces that enable interaction with reality while concealing its actual structure and properties. Conscious realists argue that perception, despite its limitations and occasional errors, generally provides reliable information about environmental structure and object properties. While interface theorists maintain that perceptual experiences systematically misrepresent reality by prioritizing fitness utility over truthful representation of objective environmental characteristics, desktop metaphor analogies illustrate how interface theory operates by comparing perceptual experience to computer desktop interfaces, where users interact with files and programs through simplified visual icons that enable effective computing while hiding the complex electronic processes, binary code, and hardware operations that actually constitute computational reality. Just as desktop icons bear no resemblance to underlying computational processes, yet enable efficient computer interaction, perceptual experiences might bear no resemblance to objective reality, yet enable efficient environmental interaction through adaptive simplification and misrepresentation of actual environmental complexity. Fitness beats truth theorem provides mathematical proof that under broad conditions, natural selection favors perceptual strategies that enhance fitness over strategies that provide truthful information about environmental properties, demonstrating that organisms using fitness-based perceptual strategies will outcompete organisms using truth-based strategies when these approaches conflict in their guidance for survival-relevant behaviors. This mathematical result suggests that truthful perception represents an evolutionary disadvantage rather than an advantage when truth and fitness provide different guidance for behavioral decision-making in competitive environments. Perceptual construction processes involve active interpretation and organization of sensory inputs through neural processing that creates coherent perceptual experiences from fragmentary and ambiguous sensory data while filling gaps, resolving contradictions, and imposing organizational patterns that enable meaningful interaction with environmental complexity. These construction processes demonstrate that perception involves substantial processing and interpretation rather than passive reception of the environmental information, suggesting that perceptual experiences result from active neural construction rather than direct environmental impression on passive sensory receptors. Virtual reality analogies suggest that ordinary perceptual experience might resemble immersive virtual reality, where users experience artificial environments through sensory displays that create convincing experiential realities, while remaining completely disconnected from actual environmental properties beyond the technological apparatus generating virtual experiences. If perceptual systems operate as biological virtual reality generators, then ordinary conscious experience might bear the same relationship to objective reality that virtual reality experiences bear to actual physical environments surrounding virtual reality users. Species-specific perceptual worlds demonstrate that different organisms perceive very different environmental realities through their specialized sensory systems and perceptual processing capabilities, with echolocation in bats, magnetic field sensitivity in migratory birds, and ultraviolet vision in insects, creating perceptual worlds that remain largely inaccessible to human consciousness, while potentially providing equally valid yet incompatible perspectives on shared environmental reality. These species differences suggest that no single perceptual perspective provides privileged access to objective reality, while all perceptual systems represent specialized interfaces adapted to particular ecological niches. Psychophysical research reveals systematic relationships between physical stimuli and perceptual experiences that often involve nonlinear transformations, contextual dependencies, and constructive processes that create perceptual responses that differ substantially from simple registration of physical stimulus properties. Color perception, for example, involves complex neural processing that creates consistent color experiences despite dramatic variations in illumination conditions, while revealing that color represents neural construction rather than direct registration of electromagnetic wavelength properties. Illusion and hallucination phenomena demonstrate that perceptual systems can create convincing conscious experiences without corresponding environmental stimuli, while revealing the constructive nature of normal perception through breakdown conditions, where construction processes operate independently of environmental input to generate perceptual experiences that feel completely real despite lacking external causal origins. These phenomena suggest that all perceptual experience involves similar construction processes that normally correlate with environmental stimuli, but can operate independently to create equally convincing subjective realities. Technological mediation of perception through instruments, virtual reality, and augmented reality systems increasingly interposes artificial interfaces between consciousness and environment, while demonstrating how readily perceptual systems accept artificial sensory inputs as authentic environmental information when presented through appropriate interface technologies. These technological mediations blur distinctions between natural and artificial perception, while potentially providing insights into how natural perceptual systems might operate as biological interface technologies. Implications for scientific knowledge involve questions about whether scientific investigation can transcend perceptual limitations to access objective reality, or whether scientific knowledge remains constrained by the same interface limitations that affect ordinary perception, potentially creating scientific interfaces that enable more effective prediction and control, while remaining equally removed from objective reality. Scientific instruments and theoretical frameworks might represent sophisticated extensions of natural perceptual interfaces, rather than methods for escaping interface limitations to achieve direct access to objective reality. The irony interfaces like the perceptions themselves. The evolutionary argument that perception evolved for fitness rather than truth suggests that human cognitive abilities, including scientific reasoning, might be similarly optimized for survival rather than truth discovery, potentially undermining the reliability of interface theory itself. If the cognitive processes used to develop and evaluate interface theory operate according to fitness rather than truth criteria, while the proposal that perceptual interfaces conceal objective reality behind adaptive illusions raises questions about whether any knowledge about objective reality remains possible if all human cognitive access to reality operates through fitness-based interfaces that prioritize survival utility over truthful representation, creating epistemic puzzles where interface theory might be self-defeating if it implies that human reasoning cannot reliably access truth about the nature of perception and reality, suggesting that understanding perceptual interfaces might require recognizing fundamental limitations in human cognitive access to objective reality, while somehow maintaining confidence in theoretical frameworks that claim to reveal these very limitations. Quantum gravity's unresolved paradoxes emerge from attempts to unify quantum mechanics and general relativity that reveal deeper conceptual problems about the nature of space, time, and causation, while forcing physicists to question fundamental assumptions about reality's structure that seem secure within the separate domains of quantum field theory and classical general relativity. These unification efforts expose irreconcilable conflicts between quantum mechanical principles that treat space-time as a fixed background stage for quantum field evolution and general relativistic principles that treat space-time as a dynamic gravitational field that curves and evolves in response to matter and energy distributions, creating conceptual tensions that resist resolution through conventional theoretical approaches, while suggesting that understanding reality's fundamental nature might require abandoning basic assumptions about space, time, and matter that underlie both quantum mechanics and general relativity. Black hole information paradox represents one of the most profound challenges in quantum gravity, by revealing apparent conflicts between general relativity's prediction that information falling into black holes is destroyed when black holes evaporate through Hawking radiation, and quantum mechanics' requirement that information must be conserved in all physical processes to maintain the reversibility and unitarity that characterize quantum mechanical evolution. This paradox suggests that either general relativity or quantum mechanics must be fundamentally modified or abandoned, while potentially indicating that conventional concepts of information, space-time, and causation become inadequate for understanding extreme gravitational environments where quantum and relativistic effects operate simultaneously. Space-time emergence theories propose that space and time themselves might be emergent phenomena that arise from more fundamental non-spatio-temporal processes, rather than serving as the basic framework within which physical processes occur. suggesting that understanding quantum gravity requires recognizing space-time as a derived rather than fundamental aspect of reality that emerges from deeper quantum informational or relational structures. These emergent scenarios treat space-time as analogous to thermodynamic properties like temperature that emerge from underlying microscopic processes while lacking fundamental reality at the most basic level of physical description. Loop quantum gravity attempts to quantize space-time itself by treating space and time as composed of discrete quanta that eliminate space-time continuity while creating granular space-time structures at the Planck scale, where conventional geometric concepts break down and are replaced by discrete combinatorial structures that evolve through quantum mechanical processes. This approach suggests that space-time smoothness represents a large-scale approximation to fundamentally discrete quantum geometric reality, while potentially resolving some quantum gravity paradoxes through elimination of space-time continuity that creates divergences and conceptual problems in conventional approaches to quantum field theory in curved space-time. String theory, extra dimensions invoke additional spatial dimensions beyond the familiar 3 dimensions of ordinary space while requiring complex compactification mechanisms that hide these extra dimensions from ordinary observation through geometric curling that makes extra dimensions too small to detect with current experimental capabilities. These extra-dimensional frameworks attempt to unify all fundamental forces, including gravity, within string theoretical descriptions, while creating vast landscape of possible compactification schemes that might explain fine-tuning problems, but also generate enormous parameter spaces with limited predictive power for observable physics. Causal set theory proposes that spacetime consists of discrete events connected by causal relationships rather than continuous manifolds characterized by smooth geometric properties, treating spacetime as fundamentally relational and discrete, while eliminating continuous coordinates and differential geometric descriptions in favor of combinatorial structures based on causal ordering relationships between spacetime events. This approach attempts to derive spacetime geometry from more fundamental causal structure, while potentially resolving quantum gravity puzzles through discrete space-time that eliminates problematic infinities and singularities. Holographic entanglement entropy connections reveal deep relationships between quantum entanglement in boundary theories and space-time geometry in bulk theories through ADS-CFT correspondence, suggesting that space-time connectivity might emerge from quantum entanglement patterns, while potentially providing mechanisms for understanding how space-time geometry arises from quantum informational structures that operate independently of classical geometric concepts. These holographic insights suggest that quantum entanglement might be more fundamental than space-time geometry, while enabling new approaches to quantum gravity that treat geometry as emergent from entanglement. Cosmological constant problem in quantum gravity involves explaining why vacuum energy density remains approximately 120 orders of magnitude smaller than quantum field theoretical predictions, while potentially requiring new understanding of vacuum physics, quantum gravity effects, or fundamental modifications to general relativity or quantum field theory that can account for this enormous discrepancy between theoretical expectations and observational measurements. This problem suggests fundamental gaps in understanding vacuum physics and gravitational interactions at quantum scales. Singularity resolution attempts in quantum gravity aim to eliminate the mathematical and physical pathologies associated with general relativistic singularities, where space-time curvature becomes infinite and physical laws break down, while potentially revealing that quantum gravitational effects prevent singularity formation through mechanisms that modify space-time structure at extreme densities and curvatures. Various quantum gravity approaches predict different singularity resolution mechanisms, including bounce cosmologies, string theoretical resolution through extended objects, or loop quantum gravity modifications that prevent infinite curvature. Time emergence from quantum gravity involves understanding how temporal evolution and causation arise from more fundamental atemporal quantum gravitational processes, while potentially explaining the origin of time's arrow and the apparent flow of temporal experience through quantum gravitational mechanisms that generate temporal structure from atemporal foundations. These approaches treat time as an emergent rather than fundamental aspect of reality, while requiring new understanding of how temporal relationships arise from quantum gravitational dynamics. Experimental challenges in quantum gravity involve the enormous energy scales required to probe quantum gravitational effects directly through particle accelerator experiments while requiring indirect tests through cosmological observations, black hole physics, and precision tests of gravitational and quantum effects that might reveal signatures of quantum gravitational phenomena at accessible energy scales. The Planck scale energy requirements for direct quantum gravity tests exceed technological capabilities by many orders of magnitude. While demanding creative approaches to quantum gravity phenomenology, philosophical implications of quantum gravity include fundamental questions about the nature of space, time, causation, and physical reality that arise from quantum gravity research, while potentially requiring abandonment of basic conceptual frameworks that have guided physical science for centuries, including absolute space-time, deterministic causation, and objective reality independent of observation and measurement. These conceptual challenges suggest that quantum gravity might require revolutionary changes in scientific worldview, comparable to those produced by quantum mechanics and relativity. The irony gravitates like the quantum effects themselves. The attempt to unify our two most successful physical theories reveals that they might be fundamentally incompatible rather than simply incomplete. While quantum gravity research designed to provide the final theory of everything instead exposes deeper conceptual problems about space, time, and reality that suggest our most basic assumptions about physical existence might be fundamentally flawed, creating a situation where the search for ultimate physical unity leads to greater conceptual fragmentation and uncertainty about reality's fundamental nature, indicating that quantum gravity might reveal limits to human understanding rather than providing final answers about physical reality. While the mathematical sophistication required for quantum gravity research approaches levels that exceed human cognitive capabilities despite describing reality's most fundamental level that should presumably be simpler rather than more complex than emergent physical phenomena, suggesting that quantum gravity paradoxes might reflect fundamental mismatches between human conceptual frameworks and reality's actual structure, rather than temporary theoretical difficulties that will be resolved through further scientific progress. The observer effect beyond physics extends far past quantum mechanics into social sciences, psychology, and anthropology, where the act of observation and study fundamentally alters the systems being investigated, raising profound questions about whether objective knowledge is possible when the very attempt to gain knowledge changes the phenomena under study, while creating recursive loops where observations influence observed systems that then influence subsequent observations in ways that blur the distinction between subject and object, observer and observed. This pervasive observer effect suggests that the scientific ideal of detached objective observation might be impossible to achieve in practice, while potentially indicating that observer-system interactions represent fundamental features of reality, rather than merely methodological complications that can be eliminated through improved experimental design or statistical correction procedures. Hawthorne effects in social research demonstrate that research participants alter their behavior when they know they are being observed or studied, creating artificial experimental conditions that differ systematically from natural conditions, where observation is absent while potentially invalidating research conclusions that depend on assumptions about natural behavior patterns that might not exist under observation conditions. These effects highlight fundamental challenges in social science research, where the presence of researchers and research apparatus inevitably modifies social situations while creating questions about whether natural social phenomena can be studied scientifically without destroying their natural character through the observation process itself. Reflexivity problems in anthropology and sociology involve researchers recognizing that their own cultural backgrounds, theoretical assumptions, and research methodologies influence their observations and interpretations of social phenomena, while potentially creating research conclusions that reflect researcher characteristics more than objective properties of studied social systems. This reflexive relationship between researchers and research subjects creates interpretive challenges where research findings might represent constructed realities that emerge from researcher-subject interactions, rather than objective discoveries about independently existing social structures and cultural patterns. Demand characteristics in psychological experiments involve implicit and explicit cues that communicate experimental hypotheses to research participants who then modify their responses to conform to perceived experimental expectations, creating experimental artifacts that confound genuine psychological phenomena with participant attempts to be helpful or to present themselves favorably to researchers. These demand characteristics suggest that psychological research might study participant responses to experimental situations, rather than underlying psychological processes that operate independently of research contexts and experimental manipulation. Participant observation paradoxes in ethnographic research involve researchers attempting to understand social groups through direct participation, while recognizing that their presence as researchers inevitably alters group dynamics and social interactions in ways that potentially invalidate observations about natural group behavior and social organization. Ethnographers must balance participation that enables insider understanding with observation that maintains analytical distance, creating methodological tensions that highlight fundamental challenges in studying social phenomena through direct researcher involvement in social situations. Double hermeneutics in social science involve the recognition that social actors already interpret and give meaning to their social situations, while social scientists provide second-order interpretations of these first-order interpretations, creating complex interpretive relationships where social scientific knowledge becomes part of the social reality being studied as social actors incorporate social scientific concepts into their self-understanding and social practice. This reflexive relationship between social knowledge and social reality suggests that social science might transform rather than simply describe social phenomena through the introduction of new interpretive frameworks and conceptual vocabularies. Measurement reactivity in survey research and public opinion polling involves research instruments that influence the phenomena they purport to measure by encouraging respondents to form opinions about issues they had not previously considered, or by framing issues in ways that influence opinion formation and expression, rather than simply recording pre-existing attitudes and beliefs. These measurement effects suggest that public opinion might be partially created by opinion polling, while raising questions about whether stable public attitudes exist independently of measurement attempts and research interventions. Longitudinal study effects involve repeated measurements and observations that potentially influence the development and behavior of research subjects over time, while creating research relationships that become part of subjects' life experiences and self-understanding in ways that alter natural development patterns. Long-term research participation might influence subject development through research-induced self-reflection, goal formation, or behavior modification that confounds natural development with research-induced change, while challenging assumptions about natural development trajectories that exist independently of research intervention. Intervention effects in applied research involve recognition that research designed to evaluate social programs and interventions often influences program implementation and effectiveness through research processes that become part of program contexts, while potentially altering program outcomes through researcher presence, data collection activities, and evaluation feedback that modify program dynamics in ways that affect measured outcomes. These intervention effects create evaluation challenges where research might improve or impair program effectiveness independently of intrinsic program characteristics. Media effects on social phenomena involve mass media attention to social issues, research findings, and social problems that can amplify, modify, or create social phenomena through media coverage that influences public awareness, policy responses, and individual behavior in ways that alter social reality through media's intervention, rather than simply reporting on pre-existing social conditions. Media coverage of research findings can create feedback effects where publicized research influences the phenomena being studied, while creating new social realities that differ from pre-research conditions. Funding effects on research involve recognition that research funding sources, funding criteria, and funding priorities influence research questions, methodologies, and interpretations in ways that shape research outcomes, while potentially creating systematic biases that reflect funding agency interests, rather than objective scientific inquiry into natural phenomena. These funding influences suggest that scientific research occurs within institutional and economic contexts that shape research directions, while potentially compromising scientific objectivity through financial incentives and institutional pressures. Digital technology impacts on observation include online research platforms, social media monitoring, and digital data collection methods that potentially alter the social and psychological phenomena being studied through technological mediation, while creating new forms of observer effects that operate through digital interfaces and algorithmic processing, rather than direct human observation. Digital research methods might change social behavior through technological intervention while creating artificial research environments that differ systematically from non-digital social contexts. The irony observes like the effects themselves. The scientific method designed to achieve objective knowledge through controlled observation encounters fundamental limits when observation itself becomes a causal factor that modifies the phenomena under study, while attempts to eliminate observer effects through methodological refinements often introduce new forms of observer influence through increasingly sophisticated research technologies and procedures that create additional layers of mediation between researchers and research subjects, creating situations where the pursuit of objectivity generates greater subjectivity through multiplication of observer-subject interactions that blur rather than clarify the boundaries between scientific knowledge and social construction, suggesting that understanding observer effects might require abandoning traditional scientific objectivity in favor of reflexive approaches that acknowledge and integrate observer influences rather than attempting to eliminate them through improved methodology, indicating that observer effects might represent fundamental features of knowledge production rather than methodological problems that can be solved through better experimental design and statistical analysis. Computational limits of scientific knowledge reveal fundamental constraints on measurement, calculation, and prediction that might prevent science from ever determining whether reality is real. As researchers encounter irreducible barriers imposed by quantum uncertainty principles, computational complexity theory, and information-theoretic bounds that limit the precision and scope of scientific investigation regardless of technological advancement or theoretical sophistication. These fundamental limits suggest that some questions about reality's nature might be computationally undecidable even in principle, while creating permanent epistemic horizons beyond which scientific knowledge cannot penetrate through any conceivable extension of current scientific methodologies and technological capabilities. Quantum measurement limits impose fundamental constraints on the precision with which physical properties can be simultaneously determined through Heisenberg uncertainty relations that prevent exact knowledge of complementary observables, while creating trade-offs between measurement precision for different physical quantities that cannot be eliminated through improved measurement technology or more sophisticated experimental procedures. These quantum limits suggest that complete knowledge of physical systems remains impossible even in principle, while potentially indicating that reality itself possesses fundamental indeterminacy rather than simply appearing indeterminate due to measurement limitations or theoretical inadequacies. Computational complexity barriers prevent efficient calculation of many physical systems, including protein folding, weather prediction beyond short time horizons, and many-body quantum systems that exhibit exponential scaling of computational requirements with system size, while potentially creating permanent limits on scientific prediction and understanding that cannot be overcome through advancing computer technology or algorithmic improvements. These complexity barriers suggest that some physical phenomena might be fundamentally unpredictable while remaining deterministic in principle, creating situations where deterministic systems produce unpredictable behavior due to computational rather than physical limitations. Gödel's incompleteness theorems demonstrate that formal mathematical systems cannot prove their own consistency while containing true statements that cannot be proven within the system, suggesting that scientific theories based on formal mathematical frameworks might encounter similar incompleteness limitations that prevent complete scientific understanding, even within purely mathematical domains that avoid empirical measurement complications. These logical limitations indicate that complete scientific knowledge might be impossible even for purely mathematical aspects of physical theories, while potentially revealing fundamental limits to logical reasoning and formal knowledge systems. Undecidable problems in computer science include the halting problem and other computational questions that cannot be algorithmically decided, even with unlimited computational resources and infinite time, suggesting that some questions about physical systems and natural phenomena might be fundamentally undecidable through computational methods, regardless of technological capabilities or algorithmic sophistication. These undecidability results indicate that computational approaches to scientific knowledge face irreducible limitations, while potentially revealing that some aspects of reality transcend computational analysis and prediction. Information theoretic bounds, including the Landauer limit and other thermodynamic constraints on information processing, impose fundamental limits on computation and measurement that cannot be overcome through technological advancement, while potentially preventing arbitrarily precise scientific investigation due to energy costs and entropy requirements associated with information processing and measurement activities. These physical limits on information processing suggest that scientific knowledge faces fundamental thermodynamic constraints, while potentially indicating that understanding reality requires energy expenditures that grow without bound for complete knowledge acquisition. Chaos theory limitations reveal that deterministic systems can exhibit behavior that remains fundamentally unpredictable due to sensitive dependence on initial conditions that amplifies arbitrarily small uncertainties into large-scale unpredictability, while creating permanent barriers to long-term prediction, even for simple deterministic systems that operate according to known physical laws. These chaotic dynamics suggest that predictability limits arise from system dynamics rather than measurement limitations, while potentially indicating that some aspects of reality remain inherently unpredictable despite being deterministic in principle. Self-reference paradoxes in scientific theories involve logical problems that arise when theories attempt to account for their own existence and validity, while potentially creating self-referential loops that generate logical contradictions, or infinite regresses that prevent theoretical completion and logical closure. These self-reference problems suggest that complete scientific theories might be logically impossible, while potentially indicating that scientific knowledge faces fundamental logical barriers that transcend empirical and computational limitations through purely logical considerations. Emergent phenomena limitations involve complex systems that exhibit properties and behaviors that cannot be predicted from knowledge of component properties and interactions due to emergence that transcends reductive analysis, while potentially creating permanent barriers to complete scientific understanding of complex systems regardless of component-level knowledge and computational capabilities. These emergence limitations suggest that some scientific phenomena might be fundamentally irreducible, while potentially indicating that complete scientific knowledge requires understanding emergence mechanisms that themselves might transcend scientific analysis. Observer limitations in scientific knowledge involve recognition that human cognitive capabilities, perceptual systems, and conceptual frameworks might impose fundamental constraints on scientific understanding that cannot be overcome through technological enhancement or methodological improvement, while potentially preventing human access to aspects of reality that transcend human cognitive architecture and conceptual capacity. These observer limitations suggest that scientific knowledge remains constrained by human nature, while potentially indicating that complete understanding of reality might require cognitive capabilities that exceed human limitations. Measurement disturbance relationships in quantum mechanics and other scientific domains involve fundamental trade-offs between knowledge acquisition and system disturbance that prevent simultaneous complete knowledge and minimal system interference, while potentially creating permanent barriers to non-invasive scientific investigation that could provide complete knowledge without altering study systems. These measurement disturbance relationships suggest that scientific knowledge necessarily involves system modification, while potentially indicating that undisturbed reality remains fundamentally inaccessible to scientific investigation. Theoretical underdetermination problems involve situations where multiple incompatible theories remain equally consistent with all available empirical evidence, while potentially creating permanent ambiguity about theoretical truth that cannot be resolved through additional empirical investigation or theoretical development. These underdetermination problems suggest that empirical evidence might be insufficient for theoretical choice, while potentially indicating that scientific theories might never converge on unique theoretical truth even with unlimited empirical investigation and theoretical sophistication. The irony limits like the knowledge itself. The development of increasingly sophisticated scientific methodologies and technologies reveals fundamental constraints on scientific knowledge that suggest complete understanding of reality might be impossible even in principle. While computational theory and mathematical logic demonstrate that some questions about reality might be formally undecidable regardless of empirical investigation and theoretical development, creating situations where advancing scientific capability simultaneously reveals greater limitations on scientific knowledge, while potentially indicating that the question of reality's reality falls among the undecidable problems that transcend scientific resolution. Suggesting that scientific humility about fundamental metaphysical questions might be rationally required rather than representing temporary ignorance that will be eliminated through future scientific progress, indicating that living with uncertainty about reality's nature might be an inevitable aspect of the human condition, rather than a problem that can be solved through sufficient scientific advancement and theoretical sophistication. The philosophy-science divide deepens as disagreements about reality often stem from different philosophical assumptions about the goals and methods of scientific inquiry, creating fundamental tensions between philosophical approaches that emphasize conceptual analysis, logical consistency, and metaphysical reasoning versus scientific approaches that prioritize empirical evidence, mathematical modeling, and experimental verification while treating philosophical considerations as secondary to empirical adequacy and predictive success. These methodological differences generate conflicting assessments of scientific theories and their implications for understanding reality's nature, while revealing that scientific and philosophical approaches to knowledge operate according to different criteria for truth. Evidence and theoretical adequacy that resist easy integration or hierarchical ordering. Logical positivism attempted to eliminate metaphysical questions from scientific inquiry by focusing exclusively on empirically verifiable statements while dismissing philosophical questions about reality's ultimate nature as meaningless pseudo-problems that arise from linguistic confusion rather than genuine knowledge gaps that require theoretical resolution. This positivist approach treated metaphysical questions about reality as scientifically irrelevant, while maintaining that genuine knowledge must be based on empirical observation and logical analysis rather than speculative reasoning about unobservable theoretical entities or abstract philosophical concepts that cannot be subjected to experimental testing and empirical verification. Post-positivist philosophy of science recognizes that scientific theories inevitably involve metaphysical assumptions about reality's nature, while acknowledging that empirical evidence alone cannot determine theoretical choice among competing theories that make identical empirical predictions, yet differ in their metaphysical implications and philosophical interpretations. This post-positivist perspective treats metaphysical considerations as legitimate aspects of scientific theorizing, while requiring integration of philosophical and empirical considerations in evaluating scientific theories and their implications for understanding reality, rather than attempting to eliminate philosophical considerations from scientific practice. Realism versus anti-realism debates in philosophy of science involve fundamental disagreements about whether scientific theories describe objective reality that exists independently of human knowledge and observation, or whether scientific theories represent useful instruments for organizing experience and making predictions without necessarily corresponding to objective reality structures that transcend human conceptual frameworks and empirical access. Scientific realists maintain that successful scientific theories approximately describe objective reality, while anti-realists argue that scientific success requires only empirical adequacy rather than correspondence to mind-independent reality. Underdetermination arguments in philosophy of science demonstrate that empirical evidence systematically underdetermines theoretical choice, while enabling multiple incompatible theories to remain equally consistent with all available empirical evidence, suggesting that scientific method alone cannot resolve fundamental questions about reality's nature without additional philosophical criteria that transcend purely empirical considerations. These underdetermination problems indicate that scientific knowledge requires philosophical assumptions, while potentially revealing that empirical evidence provides insufficient grounds for choosing among competing metaphysical interpretations of scientific theories. Theory-ladenness of observation involves recognition that scientific observations are inevitably influenced by theoretical assumptions and conceptual frameworks that determine what counts as relevant evidence while potentially creating circular relationships between theoretical commitments and empirical evidence that support those commitments. This theory-ladenness suggests that neutral empirical evidence independent of theoretical interpretation might be impossible, while potentially indicating that scientific objectivity requires philosophical analysis of theoretical assumptions, rather than simple empirical investigation that treats observations as theory-neutral. Paradigm shifts in scientific development involve fundamental changes in conceptual frameworks, methodological assumptions, and criteria for theoretical adequacy that create discontinuities in scientific knowledge, while potentially revealing that scientific progress involves philosophical revolution rather than cumulative empirical advancement toward objective truth about reality. These paradigm shifts suggest that scientific knowledge remains historically contingent and culturally relative, while potentially indicating that questions about reality's nature cannot be resolved through scientific method alone, without philosophical analysis of paradigm assumptions. Methodological naturalism in science involves the assumption that scientific investigation should be limited to natural causes and empirically accessible phenomena, while excluding supernatural or metaphysical explanations from scientific consideration regardless of their potential truth or explanatory power. This methodological constraint enables scientific practice to proceed without resolving ultimate metaphysical questions, while potentially limiting scientific investigation to phenomena that can be studied through naturalistic methods, regardless of whether reality transcends naturalistic boundaries. Scientism versus philosophical pluralism debates involve disagreements about whether scientific method provides the only reliable path to knowledge about reality, or whether philosophical reasoning, intuitive insight, and other non-scientific approaches to knowledge possess legitimate cognitive authority that complements rather than competes with scientific knowledge. Scientism maintains that scientific method provides the sole criterion for rational belief, while philosophical pluralism argues for multiple valid approaches to understanding reality that cannot be reduced to scientific methodology. Naturalized epistemology attempts to integrate philosophical and scientific approaches to knowledge by treating epistemological questions as empirical questions about human cognitive psychology and evolutionary development, while potentially eliminating traditional philosophical approaches to knowledge that operate independently of empirical investigation. This naturalization project suggests that philosophical questions about knowledge and reality should be answered through scientific investigation of cognitive processes rather than through conceptual analysis and logical reasoning that operate independently of empirical evidence. Continental versus analytic philosophical approaches create additional divisions in addressing questions about reality and scientific knowledge, with continental philosophers emphasizing historical, cultural, and interpretive dimensions of knowledge, while analytic philosophers focus on logical analysis, formal methods, and conceptual clarity that align more closely with scientific methodology. These philosophical style differences create incompatible approaches to understanding science and reality, while potentially requiring integration of multiple philosophical traditions to address complex questions about reality's nature. Interdisciplinary challenges arise when philosophical and scientific approaches to reality. Questions must be integrated through collaborative research that respects both philosophical rigor and empirical adequacy, while creating new methodological frameworks that can address complex questions about reality that exceed the scope of either purely philosophical or purely scientific investigation. These interdisciplinary efforts require developing new criteria for theoretical adequacy that incorporate both philosophical and scientific considerations, while potentially creating new approaches to knowledge that transcend traditional disciplinary boundaries. The irony divides like the disciplines themselves. The attempt to understand reality requires both philosophical analysis of conceptual foundations and scientific investigation of empirical phenomena. Yet philosophical and scientific approaches to knowledge operate according to different methodological assumptions and criteria for theoretical adequacy that resist integration while potentially revealing that questions about reality's nature transcend the scope of either philosophical or scientific investigation alone, creating situations where neither philosophy nor science can provide complete answers to fundamental questions about reality. While their separation prevents the kind of integrated investigation that might be necessary for understanding complex questions about reality's nature, suggesting that resolving disagreements about reality might require developing new forms of inquiry that integrate philosophical and scientific approaches, rather than maintaining disciplinary boundaries that artificially separate conceptual and empirical dimensions of reality, questions that might be inherently interdisciplinary and require collaborative investigation that respects both philosophical rigor and empirical adequacy. Technological mediation of reality through virtual and augmented reality systems increasingly blurs the boundaries between real and artificial experience, while creating immersive artificial environments that can be perceptually indistinguishable from natural experience, complicating traditional definitions of reality that depend on distinguishing authentic from simulated experience through technological interfaces that mediate between consciousness and environment in ways that challenge conventional assumptions about direct perceptual access to objective reality. These technological developments suggest that the distinction between real and artificial experience might be less fundamental than typically assumed, while potentially revealing that all experience involves technological or biological mediation that prevents direct access to unmediated reality, regardless of whether mediation occurs through natural sensory systems or artificial technological interfaces. Virtual reality environments create complete sensory replacement, where users experience artificial environments through technological sensory substitution that can provide convincing experiences of spatial navigation, object interaction, and social communication within entirely artificial contexts that bear no necessary relationship to external physical environments, yet generate authentic conscious experiences and emotional responses. These virtual experiences demonstrate that convincing conscious experience can be generated through technological means, while potentially revealing that the authenticity of conscious experience depends on internal coherence and sensory consistency, rather than correspondence to external physical reality that exists independently of conscious experience. Augmented reality systems overlay artificial information and virtual objects onto natural perceptual environments through technological enhancement that modifies rather than replaces natural sensory experience, while creating hybrid realities where artificial and natural elements become integrated into unified perceptual experiences that transcend simple distinctions between real and virtual components. These augmented experiences suggest that technological mediation can enhance rather than merely replace natural experience, while potentially revealing that natural and artificial elements can be seamlessly integrated into coherent experiential realities that challenge traditional boundaries between technological and natural experience. Mixed reality paradigms involve technological systems that enable interaction between virtual and physical objects through interfaces that treat artificial and natural elements as equally real components of unified interactive environments, where virtual objects can influence physical processes, while physical objects affect virtual systems through bidirectional interaction that transcends traditional subject-object and real virtual distinctions. These mixed reality systems suggest that technological mediation might create new forms of reality that integrate rather than replace natural experience, while potentially enabling new types of conscious experience that transcend traditional limitations on human sensory and cognitive capabilities. Telepresence technologies enable remote embodiment where users experience distant physical environments through robotic avatars and remote sensory systems that provide real-time sensory access to distant locations while enabling physical interaction with remote environments through technological extension of bodily presence and agency that transcends spatial limitations on direct physical experience. These telepresence capabilities suggest that consciousness and agency can be technologically extended beyond biological bodily boundaries while potentially revealing that embodied experience depends on sensory feedback and motor control rather than spatial co-location of consciousness and body. Brain-computer interfaces create direct technological connections between neural activity and artificial systems that can bypass natural sensory channels while enabling conscious control of artificial devices through direct neural signal interpretation and artificial sensory input through direct neural stimulation that circumvents natural sensory organs and motor systems. These neural interfaces suggest that consciousness can operate through technological rather than biological mediation, while potentially revealing that the boundary between natural and artificial cognitive processes becomes arbitrary when technological systems interface directly with neural activity rather than operating through external sensory channels. Artificial sensory substitution technologies enable perception of environmental information through alternative sensory modalities, including tactile displays for visual information, electronic hearing aids that process acoustic information, and magnetic field sensors that provide spatial navigation information through artificial sensory channels that supplement or replace natural sensory capabilities. These sensory substitution systems demonstrate that perceptual information can be successfully transmitted through alternative technological channels, while potentially revealing that sensory experience depends on information processing patterns rather than specific biological sensory organs or natural sensory modalities. Digital life and online existence involve increasing portions of human experience occurring within digital environments, including social media platforms, virtual communities, and online interactive systems where social relationships, creative expression, and meaningful activity occur through technological mediation that can provide authentic social and creative experiences despite occurring within artificial technological frameworks rather than direct physical interaction. These digital experiences suggest that meaningful conscious experience can occur through technological mediation, while potentially revealing that social reality and personal identity can be authentically expressed through artificial technological interfaces. Simulation fidelity improvements in technological reality systems approach perceptual thresholds where artificial experiences become indistinguishable from natural experiences through advancing technological capabilities that provide increasingly sophisticated sensory substitution, environmental simulation, and interactive responsiveness that match or exceed natural environmental complexity and sensory richness. These fidelity improvements suggest that technological simulation might eventually eliminate perceptual criteria for distinguishing artificial from natural experience, while potentially revealing that perceptual authenticity depends on experiential consistency rather than correspondence to independently existing physical reality. Embodiment and presence in artificial environments involve psychological and phenomenological dimensions of technological experience, where users develop authentic sense of spatial presence, bodily embodiment, and environmental immersion within artificial technological environments that can generate convincing experiences of being physically present in artificial locations despite remaining physically located within technological apparatus that mediates between consciousness and artificial environmental simulation. These presence experiences suggest that embodiment and spatial presence depend on sensory coherence rather than physical location, while potentially revealing that conscious experience of reality depends on experiential integration rather than external physical correspondence. Reality testing and authenticity assessment become increasingly problematic as technological mediation advances, while potentially eliminating reliable criteria for distinguishing technologically mediated from natural experience through technological capabilities that can simulate any possible sensory experience with arbitrary fidelity and interactive responsiveness. These authenticity challenges suggest that traditional criteria for reality assessment might become obsolete, while potentially revealing that the concept of authentic reality independent of technological mediation represents a historical artifact rather than a fundamental ontological distinction. Future technological integration might create seamless fusion of natural and artificial experience, where technological mediation becomes invisible and ubiquitous, while potentially eliminating meaningful distinctions between natural and artificial experience through technological systems that integrate completely with biological, sensory, and cognitive systems to create enhanced rather than alternative forms of conscious experience that transcend current limitations on human perceptual and cognitive capabilities. The irony mediates like the technology itself. The development of technologies designed to simulate and enhance reality reveals that the distinction between real and artificial experience might be less fundamental than assumed, while potentially demonstrating that all experience involves mediation through biological or technological interfaces that prevent direct access to unmediated reality, creating situations where advancing technological capabilities for reality simulation simultaneously reveal the mediated nature of all experience, including natural experience that operates through biological, sensory, and cognitive mediation, suggesting that questions about reality's reality become more rather than less complex as technological mediation advances, while potentially indicating that understanding reality requires recognizing mediation as fundamental to all conscious experience, rather than attempting to distinguish authentic from artificial experience through criteria that might themselves depend on particular forms of mediation that could be technologically reproduced or enhanced. Living with uncertainty becomes an existential and intellectual challenge as scientists and philosophers explore how to navigate life and conduct meaningful research while acknowledging fundamental uncertainty about the nature of reality itself, forcing both professional scientists and ordinary humans to develop ways of functioning effectively despite unresolved questions about whether objective reality exists independently of consciousness, whether scientific knowledge provides reliable access to truth, and whether the universe operates according to deterministic laws or involves fundamental indeterminacy that transcends human knowledge and prediction capabilities. This embrace of uncertainty requires developing new frameworks for decision-making, knowledge evaluation, and personal meaning that remain functional despite philosophical skepticism about reality's fundamental nature, while potentially revealing that uncertainty represents a permanent feature of the human condition, rather than a temporary problem that will be resolved through future scientific or philosophical progress. Pragmatic approaches to scientific uncertainty focus on the practical utility and predictive success of scientific theories, while remaining agnostic about their ultimate truth status or correspondence to objective reality. Treating scientific knowledge as tools for prediction and control rather than descriptions of mind-independent reality that exists beyond human observation and theoretical construction. This pragmatic stance enables continued scientific research and technological development, despite unresolved foundational questions, while potentially providing functional frameworks for scientific practice that avoid metaphysical commitments about reality's ultimate nature that cannot be empirically resolved through scientific investigation alone. Epistemic humility involves recognizing the limitations of human knowledge and cognitive capabilities, while maintaining intellectual honesty about the extent of scientific ignorance and philosophical uncertainty that characterizes current understanding of reality's fundamental nature. This humble approach to knowledge acknowledges that many important questions might remain permanently beyond human cognitive reach, while potentially preventing overconfident claims about scientific knowledge and encouraging continued investigation, despite uncertainty about ultimate theoretical foundations and empirical adequacy that characterizes scientific theories. Fallibilistic approaches to knowledge maintain that all human knowledge remains tentative and subject to revision, while avoiding dogmatic commitment to particular theoretical positions or metaphysical assumptions that might prevent recognition of alternative possibilities and theoretical developments. Fallibilism enables continued learning and theoretical development while acknowledging that current scientific theories and philosophical positions might be fundamentally mistaken despite their apparent success and logical coherence, creating intellectual flexibility that enables adaptation to new evidence and theoretical insights. Perspectivism acknowledges that human knowledge necessarily involves particular perspectives and conceptual frameworks that might limit access to reality, while potentially revealing that multiple valid perspectives on reality might coexist without requiring synthesis into unified objective knowledge that transcends perspectival limitations. This perspectival approach treats knowledge as inherently situated and partial, while potentially enabling appreciation of diverse approaches to understanding reality that complement rather than compete with each other through recognition of perspectival validity rather than objective truth. Constructive skepticism maintains critical evaluation of knowledge claims, while avoiding destructive skepticism that paralyzes inquiry and practical action through excessive doubt that prevents productive investigation and meaningful decision-making. This moderate skeptical stance enables continued scientific and philosophical investigation, while maintaining critical distance from dogmatic theoretical commitments that might prevent recognition of theoretical limitations and alternative possibilities that require further investigation and theoretical development. Existential implications of reality uncertainty involve questions about how awareness of fundamental uncertainty affects personal meaning, moral responsibility, and life satisfaction, while potentially requiring development of meaning frameworks that remain functional despite uncertainty about ultimate metaphysical questions that traditionally provided foundations for ethical and existential orientation. Living with uncertainty might require developing meaning and purpose that depend on human creative activity, rather than correspondence to objective reality structures that might not exist independently of human thought and experience. Scientific practice under uncertainty involves developing research methodologies and theoretical frameworks that remain productive despite foundational uncertainty, while potentially requiring new approaches to scientific investigation that integrate philosophical reflection with empirical research through recognition that scientific knowledge involves both empirical and conceptual dimensions that cannot be separated without losing essential aspects of scientific understanding. This integrated approach might enable more robust scientific knowledge that acknowledges rather than ignores foundational uncertainties. Decision-making under fundamental uncertainty requires developing practical frameworks for action and choice that remain functional despite unresolved questions about reality's nature, while potentially revealing that practical wisdom involves accepting uncertainty rather than eliminating it through theoretical resolution that might be impossible to achieve. These practical approaches might enable effective action despite theoretical uncertainty, while potentially demonstrating that practical and theoretical knowledge involve different types of understanding that cannot be reduced to unified theoretical frameworks. Educational implications of reality uncertainty involve questions about how scientific and philosophical education should address foundational uncertainty, while potentially requiring pedagogical approaches that prepare students for intellectual uncertainty, rather than providing false certainty about scientific knowledge that cannot be justified through current evidence and theoretical understanding. Education that acknowledges uncertainty might produce more intellectually honest and flexible thinkers who can adapt to changing theoretical frameworks and empirical discoveries. Therapeutic and psychological aspects of uncertainty involve understanding how fundamental uncertainty about reality affects mental health, anxiety, and psychological well-being, while potentially requiring therapeutic approaches that help individuals develop psychological resilience and meaning frameworks that remain functional despite metaphysical uncertainty that might trigger existential anxiety and meaning crises. Psychological adaptation to uncertainty might involve developing tolerance for ambiguity and uncertainty that enables productive functioning despite unresolved foundational questions. Cultural and social implications of reality uncertainty involve understanding how widespread awareness of fundamental uncertainty about reality might affect social institutions. cultural practices and collective meaning systems, while potentially requiring new social frameworks that can function effectively despite metaphysical uncertainty that challenges traditional cultural foundations based on assumptions about objective reality and reliable knowledge. Social adaptation to uncertainty might involve developing collective meaning systems that integrate rather than eliminate uncertainty through recognition of uncertainty as fundamental to human experience. The irony lives like the uncertainty itself. The quest for certainty about reality's nature reveals that uncertainty might be a fundamental and permanent aspect of the human condition rather than a temporary problem that can be solved through sufficient scientific progress or philosophical analysis. While attempts to eliminate uncertainty through increasingly sophisticated scientific and philosophical investigation often generate greater rather than less uncertainty about fundamental questions that resist resolution despite theoretical sophistication and empirical advancement, creating situations where intellectual honesty requires embracing rather than eliminating uncertainty, while developing practical and existential frameworks that enable meaningful life and productive inquiry despite permanent uncertainty about ultimate metaphysical questions. Suggesting that living well might require accepting uncertainty as fundamental to human existence, rather than viewing uncertainty as a problem that needs to be solved through knowledge acquisition, indicating that wisdom might involve learning to function effectively despite rather than by eliminating fundamental uncertainty about reality's nature and our knowledge of it. The question remains suspended in the quiet spaces between certainties, between theories and experiments, between the confident assertions of one generation of scientists and the puzzled revisions of the next, floating like a persistent whisper through laboratories and lecture halls where researchers continue their investigations while secretly harboring doubts about the fundamental nature of what they study. In the moments between measurement and interpretation, between hypothesis and conclusion, the ancient philosophical puzzles about reality's reality resurface with each new discovery that complicates rather than clarifies our understanding of existence itself. Throughout university corridors and research institutions around the world, physicists trace equations on whiteboards, while privately wondering whether their mathematical symbols correspond to anything beyond human conceptual construction. Their most sophisticated theories revealing layers of abstraction that distance them further from any direct encounter with reality itself. The quantum mechanics that describes the behavior of every atom in the universe remains conceptually mysterious after a century of experimental confirmation, its mathematical precision matched only by its interpretive opacity that leaves fundamental questions about observation, measurement, and existence permanently unresolved. In the depths of space where galaxies spiral through cosmic darkness, reality unfolds according to patterns that might be mathematical harmonies inscribed in the fabric of existence or arbitrary constructions projected by conscious observers who cannot escape their own conceptual frameworks while attempting to understand a universe that might not possess the objective structure that scientific investigation presupposes. The cosmic microwave background radiation carries information from the universe's earliest moments, while remaining silent about whether those moments involve the birth of actual space-time or the emergence of consistent experiential patterns in consciousness that has always existed. Consciousness itself continues its ancient mystery performance, generating the subjective experiences through which all questions about reality must be asked and answered, while remaining the one phenomenon that resists integration into scientific frameworks designed to study objective phenomena rather than the subjective awareness that makes all scientific investigation possible. Every neuroscientist who studies the brain confronts the paradox of consciousness, using consciousness to investigate consciousness, while remaining unable to bridge the explanatory gap between neural activity and the subjective experience that constitutes the reality of scientific thought itself. The technologies that increasingly mediate human experience blur the boundaries between natural and artificial reality, while revealing that the distinction might be less fundamental than the humans who create and use these technologies typically assume, suggesting that reality itself might be more technological or constructed than the common sense notion of independent material existence would suggest. Virtual reality systems approach the threshold where artificial experience becomes indistinguishable from natural experience, while potentially demonstrating that natural experience has always involved similar construction processes that remain invisible due to their biological rather than technological implementation. In meditation halls and contemplative spaces around the world, practitioners explore consciousness directly through introspective investigation that bypasses technological and conceptual mediation, while potentially discovering that awareness itself represents the fundamental reality from which all questions about objective existence arise. Their contemplative findings remaining largely incompatible with scientific methodologies that treat consciousness as an object of study rather than the irreducible subject that makes all study possible. Future generations may develop technologies that can directly interface with consciousness, reveal the quantum foundations of space-time, or simulate entire universes with conscious inhabitants. Yet these technological achievements might deepen rather than resolve fundamental questions about reality by revealing new layers of complexity and uncertainty that exceed rather than eliminate the conceptual puzzles that have challenged human understanding throughout history. The development of artificial consciousness might force recognition that consciousness represents a more fundamental feature of reality than previously assumed, while potentially demonstrating that the question of reality's reality cannot be answered from within any particular reality framework, whether natural or artificial. The uncertainty that permeates contemporary scientific and philosophical investigation of reality might represent not a temporary state of ignorance that will be resolved through future progress, but a fundamental feature of the relationship between consciousness and existence that ensures that questions about reality's reality will continue to evolve without reaching final resolution, requiring each generation to develop new ways of living meaningfully, while acknowledging rather than eliminating fundamental uncertainty about the nature of existence itself. As research laboratories grow quiet and researchers pause between experiments, between calculations, between the confident presentation of results and the private acknowledgement of persistent mysteries, the question of reality's reality continues its patient presence, neither answered nor abandoned, but carried forward through the ongoing human enterprise of seeking understanding, while somehow finding ways to live meaningfully, despite the permanent possibility that reality might be very different from any human conception of what reality should be.